Hey! Looks like we are live, and I've got a show lined up for you this evening. We have, I believe there's 4 people waiting to join the stream, so hopefully we'll get something sorted very soon. A few shout outs to some of the people that are in, because I haven't called them yet on Skype, by the way. But I will do, promise you, I will call you in about 2 minutes. So, we have Adam Meakin in YouTube, who actually went and spammed the link in Globebusters. Thank you very much for doing that. I don't think Bob will be too pleased, though. Elvis, nice to see you in. Rakia Life, Rune, Domesticated Primate, nice to see you in. Jimbo, Arwin, you can join, by the way. I have added you to the group, so when I call you in a moment or so, hopefully you will join. Let's see, who else have we got in? Flat Phrase and 5 Angels, nice to see you in. Without question, CGI, Ranty, Guav, too many people popping in right now. Right, let's get this show on the road. Let's give a call. Let's see who picks up. Just bear with me, guys. Hello.
Hello.
Who have we got there? That's Brian. That's Brian, isn't it?
Yeah.
Howdy doody. How's it going, mate?
Not too bad, yourself?
Yeah, it's going good. It's going good. Thank you very much. So you wanted to do a little presentation as well, I believe. Just a few minutes worth.
Oh yeah, it's just a couple of things, just to address something that I heard on. I've been listening to Jose's the past couple of days because of the platform photograph. I normally don't listen to Jose's, but very much, but because of that, I was listening to it, and there was some stuff brought up there today by a couple of the people on Jose's, and I just want to show a few things just to refute what was said. That's all. It's only a few photographs. That's all.
Okay. So, yeah, that's fine. No worries. Well, before too many people pop in, Adam, yes, I have actually invited you to the call. So if you want to join Adam, no problem. He's there. Perfect.
Hey, Adam.
Gleam, I saw you in the chat, so I have added you to the call as well. So if you want to jump on as well, that would be great. How's it going, Adam?
Can you hear me?
I can.
Evening, guys.
Hey, Adam.
Yeah, Brian, how you doing, mate?
Not too bad, lad.
Good. Bear with me a sec, Randy, because I'm just switching over my PCs. So that's why I thought it'd be good if I get on a Skype call and check what I'm doing. But I've just realised for some reason my headset's plugged in, not my thing. But yeah, but ignore me for a bit. I'll come back as soon as I've got 2 secs.
Okay, no worries. Pop yourself on mute. Brian, if you want to do that presentation, then you might as well crack on with it now before the panel fills up.
Yeah, that's fine by me.
So I think we've got a guy called Carlos coming in. He's a globe earther.
I know.
You know Carlos? Oh, right. This should be interesting then.
Yeah.
Okay.
If you want me to, do you want me to get started on it now? Just right at the start.
Of course. Yeah. Sure. Let me just transition you across. If you want to start sharing your screen and.
Second now. Okay.
Right, there you go. Right, I'll pop myself on mute whilst you do this, and then hopefully we'll get the rest in.
Okay, on the ball. I want to take about 7 minutes, I'd say, anyway. Okay?
No worries, fire away.
Okay, thanks. Okay. This is going to be in response to... I was listening to Jose's today, and I heard Blue Marble Science, which is Big Blue, as they call him, saying that he was looking at he was referencing the platforms photograph, the Black Swan photograph, and he was saying that how from a higher elevation, when it was from a higher elevation in that video, that you could see more things than when they were at a lower point in the elevation, when they were down at 1 foot elevation, that there was more stuff being able to be seen. And he was saying, how is it possible for something to be hidden from the bottom up? Basically, is what he was saying just because your camera height is lower. Now, most people out there will understand this if they're on the flat earth side already, that it's down to the angle of view. Okay, and your angle of view will create the diffraction limit, which is what the horizon is. The horizon is the diffraction limit. It's the most easiest one to reference. So I'm going to show here something I showed in a presentation recently, but this is just a very simple. This is a very simple version of what he says. He doesn't understand how it's possible to happen. This is a floor in our house, and it's just a wooden floor. And these are two objects: a jar of olives, the bigger object, and some pepper or something in the orange one there. And I'm going to show you how, with distance, the jar of olives will shrink in size and will start to disappear from the bottom up. Okay, so there is the first photograph. There is the bottom of it disappearing already, right? The bottom of the jar of olives should be a glass bottom, but it's not there because of the angle. I have my camera height low. It's about half an inch or maybe a half an inch to an inch off the ground, and you can see that because the jar of olives is in the background, its angular size has changed. It has been slightly occulted by the pepper at the front, and the bottom of it is starting to disappear. We'll go on to the next photograph. Now it's been really occulted, and you can't hardly see it, and that shows the massive angular size change and visual occultation that can happen. This one is not so relevant, this photograph, for my point. Now on to the next one. Now you start to see, again, the bottom of the olive jar is disappearing. Okay, and that's down to the fact that I'm so low to the floor. You can see how low I am, about half an inch to an inch off the floor. So you can see how low I am, and that proves that the lower your angle of view is, then the more likelihood there is for the diffraction limit to start happening. And that's what's happening there. It's like as if the olives have gone over the curve, but they haven't. The floor is just a flat floor. You can see all the floor behind it in other photographs, but here it seems to be disappearing from the bottom up. Okay, and this one, again, this is another one. It shows it disappearing from the bottom up. Now, that looks like it's gone over the curve. These were two buildings at a distance, okay, or two, let's say, if you treat the orange object as the bridge in Miles Davis's photograph from Traprain Law, and you treat the olives as Carnock Hill, then the assumption would be it's gone over the curve. But it hasn't. It's changing angular size. That's all that's happened. And in this situation, to answer Blue Marble Science's question on Jose's today, although it wasn't addressed to me because I was just listening, he said, how can things disappear from the bottom up just because your camera goes lower? And the reason is because of your angle of view. That's what it is. Like I think it's a Good Times for All. I have the name. It may not be Good Times for All. The 2-hour presentation on why this happens. On optics and why this happens. So there it is. There is a physical demonstration of that exact thing. Okay, of that exact thing happening. A physical demonstration of things disappearing from the bottom up. So that was from the bottom up due to the fact that my camera height is close to the floor. So this is the proof. This is real stuff. It's not. This is done with real things in reality. Okay, so I'm showing it. It doesn't matter if it's small or big, it'll work the same. Actually, bigger things, because if you're outside with atmosphere, there's more likely to be compression. So it's more likely to happen with bigger things because they're outdoors, and you have the atmosphere to deal with. Now, the next thing I'm going to go on to is, this. Okay. Now, Slice Barkane, although I don't know the person myself, so I'm saying his name, but I don't know the man. I've not spoken to the man. He came on to Jose's and it was shown how at his height, which was about 300 meters above sea level, there was a building in the distance. I don't know what distances the building was. These group of buildings. And at the top of one of these buildings was about the same height as his eye level was. That was about 300 meters above sea level as well. Now, in the background of these buildings, there was a group of hills that were 500 meters above sea level. Now, the hills looked to be as low as the top of the building, okay? And he was saying, how is this possible on a flat earth? How is this possible to see these hills in the background being the same height as the top of the building? This is what he was saying. And it was only just angular size change. So here I'm going to demonstrate angular size change. My camera height, okay, is actually just over the top of this. I've zoomed to this. I have zoomed to this because I have my camera height with a cover on, my camera with a cover on it, an iPhone 5, and I have it turned upside down. And my camera height, these are 1/2-inch blocks. These are all 1/2-inch blocks. This one here is the same size as this one, and them there at the back, they're all the same. They're all 1/2-inch. Some of them are longer than the others, but they're all only 1/2 inch in height. My camera height is actually just over the top of this block here. You're looking just over the top of this block, okay? This one and this one in the background are exactly the same size, right? Now I'm going to show you the next photograph. Now, you can see here, I'm just going to try and make it a bit bigger. You can see here that this line basically looks like a dead straight line, going on a straight line from here to here, okay? And it's going over the top of this block at the back, right? This is happening due to angular size change, okay? That's why this is happening. It's down to angular size change, right? And this was, I just wrote into the comments, it's just angular size change. That's what I wrote into the comments. Now, I don't think anyone saw it, but there was other people on the show that were arguing for the same thing. Now, I didn't get the chance to keep listening to the show, but I just had to correct this. This is why the hills in the background, a 500-meter hill in the background of a 300-meter high building can seem to shrink to be the same height. Because in frontal view, you get angular size change. And you also get compression in front-on view. You won't get it in an orthographic view, as in you won't notice. It might be both objects might be compressed on both left and right of you, but you won't notice one being more compressed than the other. But you will notice. You will notice it with front-on view. With frontal view, you will notice that there is compression and there always is angular size change. Now, so this completely dissolves any out curve in that photograph. Because it's the same thing as the Mount San Jacinto photograph. It's like Mount San Jacinto is being occulted by Los Angeles. The photographer in the Mount San Jacinto photograph is being occulted by over 100 foot by the city of Los Angeles in his view. And he also has a 124-mile distance between him and Mount San Jacinto. And Mount San Jacinto, his camera is slightly tilted up because of the occultation, and Mount San Jacinto has disappeared not disappeared, but has gotten very small due to angular size change. And he's also down to the type of lens he's using, which I'll show in a minute, right? How there's a difference, it depends on what type of lens you use. But so this answers Sly Sparkane's question, and Miles Davis or anyone else that wants to make that claim. Right, this top of this block here is the same height as the third block up here at the back. There's 5 blocks, and that's the same height as the third block up if I do a straight line. But technically, it's actually not, because technically in a straight line, the straight line is actually from here at an angle to there. That would actually be the straight line, because I'd have to follow a perspective. I would have to follow then a perspective straight line, not a straight line over the top. But it looks like it's a straight line over the top, and it looks like this one is smaller than that one, but it's not. It's just angular size change has happened due to frontal view. But what happened? This was proven. What I'm going to say here was proven by Samuel Rowbotham in the Bedford Levels canal tests, as he showed that angular size change was part of that by aligning his telescope up with the first 2 markers. And he said if the markers after that fell below his telescope crosshairs, then that meant that yes, there was curvature and it's possible that the world was a globe and not flat. But he proved what he was saying was correct, because when he lined up his crosshairs of his telescope, with the first 2 markers, all the other markers lined up as well. So, but if he lined it up with just the first marker, all the markers seem to disappear and below his line of sight, as this would be his line of sight here in a straight line, what appears to be a straight line, and this would be all the markers here disappearing. If I had more blocks here, it'd be like the same markers just disappearing and disappearing lower and lower below his line of sight.
So what you're saying here, Brian, is that you need two markers to actually get your line of sight. You can't just use one.
Yeah, well, if I wanted to just exactly, Randy, if I wanted to actually put that in a straight line, it would go from here down to the top of that block there. That would be a straight line if I wanted it to like that, because that block is not smaller; it just looks smaller. So you need 2 markers to get a straight line. You can't just have 1 marker. You need 2 markers, at least 2 markers, and the rest will line up. And that's what Samuel Rowbotham proved. Now, I haven't read Samuel Rowbotham's book, but I know some certain bits, and he proved that point. Because what's wrong is that they're taking observations on the globe side and looking in a straight line, and they can't understand why the bigger thing in the background has gotten smaller in just a straight line. But what they're not realizing is that's not actually just a straight line. Because
that makes sense now. Now that you've actually put it like that, that answers a lot of questions.
Yeah, that's all that's happening. what was the Moyes Davis? I said to Moyes Davis, I said, if you want to prove that the Carnock Hill has actually gone below the curve of a globe Earth, I said, all you have to do is go over to there, which is not too much of a massive distance from where he is. Go to the top of Carnock Hill, I said, and take the same observation back the way. And then if the bridge stanchion is still in your eye line, then you know you have a case. But if it's not, then you don't have a case. And he never did that. And I knew he never did, and he never would. Now, he said something to me one time, and I don't know how true it is, but he said something to me about a flat earther supposedly went up to 210 metres up Carnock Hill and looked back towards Traprain Low. And this is what he said. And he said he got the same observation the opposite way around from 210 metres, which would be the same height he was at. Now, I don't know if that actually would be true. He said something like that in comments to me one time. But to me, that means nothing. It's like I have no proof that ever happened or didn't happen. And it actually supports flat Earth anyway. But I have no proof it did happen, so I can't say for definite that happened. But I did say to him several times to go up to the top of Carnock Hill and take the same observation back the way. Because the very first thing I said to Moyes Davis was, the very first thing I said, I saw his video within 20 minutes of it coming out, the original Traprain Law video he brought out. And I told him, I said, it's just things get smaller with distance, Moyes. That was it. And he didn't want to hear about it. But this is the proof. Because as I said, Ranty, if I wanted that to be a straight line, I would go from here down to there, and then down to the very bottom one here, it would appear to be at an angle. I'll actually do it with this one right now if you want, live. Okay, let's go into annotate, go into line. Okay, I'm just going to do here, right, and here, and I'll just do to that. Just that much. Okay. Now, I might change the colour just to make it a better colour. Maybe yellow is better.
Are you watching this, Adam?
And I'll do the same at the bottom. I think Adam's on 9.
Right, I'm back in the room. So I am watching now. Sorry, mate, I had my head under the bench. You know when you're wiring up your bloody computer, you're having to stick USB in upside down. Not USB, you being upside down as opposed to it. Yeah.
That happened to me today. I stood up with my headphones in and snapped them off completely. So I've got a new pair in now. And then the boiler went. Literally, the boiler's broken. So I'm in my my dressing gown. As well as everything else. I've got a hat on right now because it's actually only 6 degrees inside the house.
I did notice the dressing gown. I didn't want to. There's nothing wrong with being cosy, man.
Normally, I wouldn't be too bothered, but normally I've got it around 22 degrees. So from 22 to 6, it's a bit of a comfort change.
No, it's bloody freezing, isn't it?
So Brian's doing this presentation here. He's basically showed that Miles Davis's presentation, when he's just using one fixed object to line his camera up to, isn't working. Perspectively, you do need to have 2 objects in the distance that you're lining it up to of the same equal height, and then you'll get a level. If you use it from just one, you're not going to do that.
Yeah, because you can't guarantee the viewing angle. The secondary point along the z-axis into the picture, as it were, it is a requirement. Otherwise, all you're doing is getting the observer's eye to meet the top of any point. Well, that doesn't. It's the secondary point that you've got the same height in the distance that allows you to level your eye almost, isn't it? It's you require the 3. The center point is almost a pivot, isn't it?
Exactly. Because that's what I was saying. Samuel Robotham did is he lined up the first 2 markers on the along the canal, the Bedford levels, and that's how he proved it was angular size change. I actually said this to, is it Jesse Kozłowski? He's the surveyor on the Globe side. And I said this to him. He had an observation across water where it was 7 miles away from him or something like that. And he had a post that was exactly the same height as the very middle of the lens of his theodolite, and he was showing how it was below the crosshairs in a straight line. He was showing how when he looked in a straight line, it was below the crosshair. So he was trying to say it went below it was going below the curve of the Earth kind of stuff. And I said to him, no, it's angular size change, because this line here, I just highlighted, this line here was the direction of his eye line, but this line here is the direction he should have been, is the true direction, because this one here looks like it's in a straight line, but it's looking out over the top of an object that has just been under the effect of angular size change. That's all it is. But this line here would be a more true angle, a more true line of sight, because this is actually a true straight, but it doesn't appear that way. It appears like this one here is the true straight line, but it's not. And this is the mistake people on the ball side are making. I'll just go back to this other photograph a second, just show you here. Dean, who was Stingray, he might be coming in tonight, I don't know. Dean said that you'll only get this effect of something like that being lower than the line at the top of the of whatever you're looking at, if your camera height is below this object. Now, my camera height is actually above this object. I'll just show you. Right, sorry. My camera height is actually just over the top of this object. If you can see, sorry, this is halfway. This object is halfway up in this frame, in this photograph. My camera height is, and I can prove this, that my camera height is just over the top of this object. So what Dean is saying is that this object here should be right along this line as well. But he was showing this. He showed this with 3D modeling software. And the problem is that he's modeling reality within software, whereas I'm modeling reality with reality. And what's happening? He showed the top of the things he had in his software, and he lined them all up. But the bottoms were not lined up. The bottoms were still at an angle, as like in this one. The bottoms were still showing this, but the tops were all lined up like this in a line.
So hang on. Sorry, can I just intersect? So let's be clear here. We're basically saying that Miles Davis, when he lines up, what is he looking at? He's looking at a tower, isn't he? Is he lining up with a tower?
Yeah, he's looking at the bridge stanchion, which is about the same exact height.
Right. So he's using one object. He's using one object to get his bearings from. And what you're showing here is that you need two of equal height to line them up before you can get a true horizon.
Yeah, you have to, because like when we see an horizon, we see the sky and the ground that seem to meet each other. And if you look at these angles, that's exactly what's happening. As angular size change causes that. What Miles Davis and the rest of them are doing is they're measuring a background object in a photograph off of a foreground object. And because they're doing it with very big objects at a very big distance, they're calling it the Earth curve. But the problem with that is I can show with very small objects the exact same thing will happen. It's just the exact same thing. You don't need big objects to show it. Small things the exact same thing will happen, but it has nothing to do with Earth curve. But they're calling it Earth curve. Like Sly Sparkane was there today on Jose's, and he was showing a 500-meter hill that was at the background of a photograph with a 300-meter high building in the foreground that was about the same height as he was at, and he was showing how can the hills be at the same height as the building if the Earth was flat. It's like it's angular size change. That's all it is. If you put the whole lot into orthographic view, then him and the top of the building would be the same height, but the hills would be higher. It's angular size change, and it's like it doesn't matter big or small. Perspective works exactly the same. So you can't just look you can't look at an observation and measure something in the background off of the foreground, because you are completely, and then call it Earth curve, because you're completely negating the fact that there is angular size change happening. So they're all looking at this line here in this way, and they're going, oh, this thing went over the curve of the Earth in their belief. But they're not. That's not a correct line. The correct line of view is from here down to the top of that and on down. So angular size changes is important, and angular size change will differ as well with compression, and compression will differ throughout the day or throughout the different days and with different lenses. I just show one thing there. which one is just showing here? Now, if you can see it, this is Mount San Jacinto taken from the same location, but the same photographer, but just with two different lenses. Now I'm going to show you another four. If you can see, I've matched up Los Angeles here, and I just show how much I matched it up. These two here, these two buildings are from those. There is the two buildings that's matched up equal size. The same building matched up equal size. I know it might be hard to see. I'll just make it bigger. Sorry. There's the same building matched up equal size in both photographs. Now I'm going to show you the next photograph. And in this photograph, because it's with a different lens, it's still showing angular size change, but because it's with a different lens, it shows as if it's higher than in this photograph. But he's from the same location, the same distance, same camera height. Yet in this one here, he has a different view due to a different lens.
What do you think about this, Gleam? Because you've seen this sort of stuff before.
Yeah, check. Is my mic on?
Your mic's on, all good. But what do you think of this?
Yeah, with the Mount Jacinto, other people have done analysis and they've basically said that there is a lot of that mountain missing. Now, as well with that, on top of that, obviously the original analysis showed that there was compression happening because it actually compresses in distance-wise. He actually pinpoints certain peaks. So,
yeah, but Liam, what they're not taking into account is the fact that Los Angeles is 100 feet above the photographer. So,
definitely,
for start, Jay Tolan has to tilt his camera slightly. But there's something else. When people, that thing you're talking about, I'm just going to show you something here. See this section here?
Yeah.
This is the section they're saying this is the section here that they're saying that Jay Tolan is seeing, right? That's all he's seeing. This is basically what on Metabunk. This is what they were trying to do. This was the debunk that was brought out. Below you here is taking Los Angeles out of it, just showing the exact amount of Mount San Jacinto. I've lined it up with this photograph at the top. Now you can see this over here, this peak over here, and that peak here. I think it's the Traquise peak or something like that. You can see both of them lined up together. You can see these hills here and these hills here all lined up together. Does that look like he only saw that much of the mountain?
No.
Yeah, this is the problem. It's this level of...
No, I understand that.
Could I just ask a...
Yeah.
Just not on what you're saying, Brian, but because obviously the point of it, I assume there's a baller point here that's they're trying to use this principle of alignment and perspective and to apply it to massive distances. Because for me, as you've talked about a few different effects, particularly compression, but there's actually probably the best that, Rumpus's lighthouse with the wavy lines to the viewer's eye.
Yeah.
That's probably the best example I could give to kind of demonstrate how you can't really use it. Whilst it's fine and perfectly reasonable to apply this across a kitchen worktop, this alignment principle, when you're getting your confirmation of alignment from the optics that you're analysing, and it's subject to all the refraction and all the multitude of wobbles and wiggles and movements, there's no way in which you could align that device optically when you can't guarantee that the image is exactly where you think it is.
Or whether it's distorted by being magnified, being sunk, loomed. Exactly. There are many, and you can apply. You can apply whatever concept you want. It's the same when it doesn't match exact geometry for each model. Each model has to come up with refraction to account for it. And I say a lot of long shots are not worth analysing because they've got lack of information. Because any temperature inversion or any temperature change, massive temperature change obviously, can do so much to the actual image. And it's exactly that.
What I would say though, Liam, is that a long distance, like I would have to kind of disagree with you there now, because a long distance shot like of Mount San Jacinto, as we see, as it's done, is not possible. It's not possible.
I do agree. I do agree. Yeah, even with refraction. No, I do agree.
There is an alignment of what he saw, what Jay Tolan saw of Mount San Jacinto, and there's this other photograph of Mount San Jacinto, and you can see that he saw about half of Mount San Jacinto, and if you take it that this photograph was taken from obviously it was taken from a different location, probably more closer up, and they didn't have Los Angeles in the way. And you can take it
topology
is occulting him, and there's angular size change going on as well.
Yeah, definitely.
You can understand, and to think of it like this, as I said in a presentation recently, if you got in a car in Point Dume in Malibu, and you had an unimpeded straight line drive from there to Mount San Jacinto, you would be driving for 2 hours at 60 miles an hour, right, non-stop, unimpeded, with no cars or anything else in your way. You drove for 60 miles an hour in a straight line from Point Dume to Mount San Jacinto, and you still would be a couple of miles away from it. So that's a 2-hour drive at 60 miles an hour. That's an awful distance to see.
Yeah, definitely. No, I do agree. And I've done one on Rory. You remember Rory?
Yes.
Yeah, Jack and Rory.
Yeah.
Owes everyone $5,000. But he exactly that. He said, this cannot be represented on a flat Earth. And there were several mountains. It was the full range of Seven Sisters, Mount St. Helens, and Rainier. And he said no one could represent it on a flat Earth. And it was easy to represent once you understood the actual topology of the land. The observer had, I think, the natural lay of the land. The observer had 1,500 meters higher than where the prominence of the likes of St. Helens and Rainier are. So it is, you've got to account for everything, and that's the thing with a lot of these long distance ones. You'd need things like temperature profiles. You'd need GPS, in as much as you don't need GPS coordinates on a globe, because they can easily be applied to a Cartesian coordinate system.
Yeah.
But you would need to understand that if Jay Tolan, or let's say not even Jay Tolan, but his friend was halfway up that mountain and shone a mirror, I know that's completely unrealistic and something like that, but you'd see a flash where he was, and then he recorded his altitude, then you would have empirical sort of like double backup evidence to say, yes, this is how far I was up there, this is how much is hidden, and this is how much you would expect to be hidden based on the perspective and the hidden topology of the city in front. So I fully get it, but analysis has got to be all or nothing. It's always half job by the globe earthers, and I fully agree with you on that.
Well, if you look at this photograph here, I'm just going to zoom in to the side of it. See this hill here? See, with the best I could match it up with this other photograph, it only looks like Jay Tolan has seen only about half of Mount San Jacinto. But this hill here is actually this hill down here. Now I've matched that up as best as I could with the top part of the bottom photograph here, with this part of the photograph they were using on Metabunk. I've matched this one up with best I could with that, trying to make sure that it was all aligned up in correct as best as it could. So this was somewhat exactly the same as this part and blah blah blah. But this part here is still showing in Jay Tolan's photograph, and this part here is this place down here and this place down here. So it's obvious that Jay Tolan has seen even more than half. He's seen hills to the left of the mountain here that they're not accounting for anything. So he's even seen more. It's compressed. It's definitely being compressed, because he's even seen more of the mountain than even it looks like here.
Well, the mountain that you don't see is just hidden in some kind of mist, probably, or low-lying cloud.
Yeah, well, I mean, it's all occulted by the city of Los Angeles has them occulted anyway. It has them occulted anyway. I'm just going to show here, and I have something to show you about the St. Helens photograph. I'm going to show you. This is what was on Metabunk, And I won't name names because there's no point. I don't matter. People can go and find out who they are. This was the amount that they said Jay Tolan could see of the mountain of Mount San Jacinto. Whereas these hills over here are them hills here and them hills here. He was obviously seeing even more of Mount San Jacinto than even I'm showing here. It's just I didn't want to go further with it because people would then start arguing with it on the ball side and say I'm only messing around or I'm making it up. So I'm showing here that he's definitely seen at least half of the mountain. But this box up here is the bit that they were trying to say on Metabunk, that this is the only bit that Jay Tolan was seeing. Like, that's complete and utter lies. That's totally dishonest.
Yeah, no, you can see the chip out of the left-hand side.
Yeah, you can see it.
You can match it, and the V shape on the right-hand side. It's you can definitely see it's right further down. I know exactly what you're talking about. I think it was 10,000 foot or something, and they were saying 7,000 was hidden, 4,000 was shown. Whereas I remember it. I remember the whole argument when it first came out. And salute Jay Tolan. Either way, he's cool.
Well, the problem they have is that he'd have to drive at 16 miles an hour for 2 hours in a straight line unimpeded just to reach that location.
Yeah.
So that's pretty massive, isn't it?
The first thing I did when I saw it is actually go on Google Earth and stand where he said he was, and actually saw he's got a little sign there or something from memory.
Yeah.
And you look across and you can't even see any of the topology, even though it's all in 3D where it is.
Yeah.
You can't even see any scenery, any mountain. You have to zoom right in at least halfway to start seeing the city appear, and then the mountain you don't even see until later on.
I'm just going to show you something here. Where are we? I think it's in here. Yeah. It'll be one of these. 1 second now. I'm going to show you something that I showed in my last presentation, but this is very strange. Open these. Right. Where are we going? Right. Yeah, this one. Is it this? No. Which one is it? Sorry, that isn't it? There it is, I think. Now, according to Google, right? Google Earth, right?
Mm-hmm.
Sorry, this is Google Maps, I think it is.
Yeah.
The distance from Point Dume to Mount San Jacinto, which I have shown here on the left, I just make it bigger if I can, right? This is the distance, Point Dume to Mount San Jacinto, right? I'm just going to make it big down here so you can see. They have it down as 244 miles.
Yeah.
That's a pretty massive difference. I don't know what's going on there, but I added that in. I don't know how true it is or not true. But what I did do is, if you take this into account, I'm just going to show it's right across the US, right? There's a direct across the US line, and they're saying it's 2,000. Let's go in. 2,239.34 miles straight across from at that point from west to east, right?
Yep.
Now, does that small line that was coming here, does that look like, I just go back to where is it? Does this look like it's only 124 miles? If that other one is 2,239, maybe. It's
I'd say it's at an angle.
Sorry?
Yeah, it's just because it's at an angle. Yeah, I would say so. It's them. Obviously, a flat projection will distort. So yeah, it will be, because it's great circle and stuff like that.
I don't know why they put it down as 244 miles, because that's what they're calling it, from where his location to that. I mean, that's not even like a small. That's not like adding or subtracting 2 or 3 miles. That's like adding another 100 odd miles to the full distance of it, which I thought was kind of strange.
Yeah. Okay. Yeah.
You remember you were talking about the Mount St. Helens photograph?
Yeah.
I actually did. I actually have it here if you want to see it. I did a video and I scaled that down. I scaled it down. What I might do is I'll unshare my screen, I'll go and find it, and I'll bring it back and I'll share it again. And I scaled that down. I might be just be able to find it here. I scaled it down and I got that exact thing on a flat floor.
Yeah, I think Antonio did it as well. When Conspiracy Cats was saying about the side peak. You remember the side peak
the
thing?
side peak. Yeah, and I know exactly what that's about. But where are we going? Clothes. Sorry. I find the video here now. This one it is.
But you know that map discrepancy that you were just on about? I think that's the Martin Luther King effect. It's kind of like the Mandela effect, but it's changed again, and maps are a big thing in that.
Yeah, there's something very strange going on there. I don't know why it's saying 244 miles, but it is. But that's what they're saying it is to Mount San Jacinto, and that's very strange. That it's I don't know. It kind of makes me wonder: are we getting proper distances at all? But even if it's only on 124 or whatever, 123, it's still far too far to be able to see on a globe.
Have you quadruple checked the actual GPS coordinates? Because there could be a couple different ones called the same thing.
No, I didn't go that far. I just threw it in there as an anomaly. Do you know, rather than trying to fight for it, because it's not something I can prove. Rather than trying to fight for it, I said I just throw it out there and see if someone else might know a bit more and might be able to. Because I'm not in a position to test it either, because I'm not in California. So
same.
This here at the background in the front is Mount St. Helens, right? I scaled it. In the background is Mount Rainier. Okay. Now my camera height here is not as low as it should be because I couldn't get any lower. If I could have got this lower, then that side, let's call this part here the side peak. That would have been lower again because my camera height would have been lower. I'm literally just at half an inch high. It is as low as a camera height as I can get. And I should have been. I think it was something like. Maybe a quarter of an inch or less high, something like that, for it to be correct with the height of the cameraman. Okay. Sure. Now this is all scaled in distance. This is the exact distance the cameraman would have been scaled down from Mount St. Helens. And that's the exact distance in the background of Mount Rainier would be from Mount St. Helens, and the exact distance from Mount Rainier to the cameraman at the time. The only thing I couldn't do here was drop my camera height lower because I just physically couldn't do it. I'd have to actually dig a hole in the floor. I tried different ways. I tried to go back away a bit from it and move forward. I tried all kinds of stuff, and I just couldn't get it any lower. But if I could have got it lower, then that would mean there's more visual occultation, which means the visual occultation will make the bigger thing in the background, because I have to look up the way more. It will cause that to sink more in the background. Sure. So this side peak will be even lower. Now, if anyone wants to look at the comment section in this, Ruhif had a thing with me about it, and he had a bit, and he couldn't, he had a go at me basically, but he didn't prove anything. I told him, I said, if my camera height was even lower, you'd see less of that side peak. He was saying, but you can still kind of see the side peak or some nonsense like that. I said, if my camera height was the height it was supposed to be, then you wouldn't see that side peak at all. And you can see at the bottom here of this block, that's the floor right there, in a dead straight line along there. So that's on a flat floor, scale down. There is your Mount St. Helens and Mount Rainier photograph. As I said, if I could get my camera height lower, I would have got it lower, and it would have only helped me. So, he was kind of saying, I don't know what he was saying. It's in the comments. It's nonsense. But someone else maybe said, you didn't have a camera height where it's supposed to be, because I say it in the video that I should have my camera height lower. And people were kind of saying, I don't have a camera height where it's meant to be. I said, yeah, but if it was lower, it would only help my case. If I could get it to where it's supposed to be, then it would help my case. So there's nothing for, those people, and Ruhif said, how do you know that your floor is 100% flat? I said, does it look like a globe out to you?
That's the classic.
Yeah,
that's the classic.
Exactly, yeah, absolute nonsense.
I've done it. I've done this exact thing. I've done this exact thing with cigarette packs with Bearded Devil. I don't know whether you've seen him, Erebus. Yeah. I basically said, look, you can obstruct something halfway if you have it double the distance. And I use cigarette boxes, and I won't load up my screen and show you all the photos. There's hundreds of them, but I literally showed that if you put a cigarette box on top of a phone it actually falls perfectly in line with the top of a side-facing cigarette box. So I've done double the distance, and it showed exactly what you showed there, where more than half of it is hidden because of just distance, and it's two cigarette boxes in the background, double the distance, double the height, and it works. And this explains exactly what Ranty's been going on about, exactly what a lot of people have been going on about on viewing over water.
Yeah.
Where this is could be the effect of a swell, could be the effect of a high tide, could be the effect of a massive wave near the object. And that ship there, you know, the ones that you see where they've got a ship in the foreground and it's in full, and then you've got a ship in the background that you can only see the tops masts.
Yeah, the angular size of the swell is more than the ship in the background.
That's it.
I have that image ready to show, actually. Because
I'm going to share my screen here. I literally, but just before I go, I just before we go, and I'm going to go straight to Ranty's, is these are all 1/2-inch blocks. So that's a 2-inch piece at the background. So this is a 1 and I think this was 1.5 almost 1.5, or just under 1.5 inches. That was the correct height, just under 1.5 inches. So you can see with visual occultation and angular size change, how this shrinking in the background. But you can see the bottom of it. Now, I actually scaled Miles Davis's photographs, but I couldn't scale the full photograph because he's at such a distance. I literally didn't have enough space in my house. So I had to scale it in such a way where it was like as if I scale it the way of the photograph I saw. So I scale it as if it zoomed in to the bridge, which is what the photograph he actually shows. Because in his actual position, the bridge is very small until he zooms to it. Yeah. You know, he's got a pretty good camera. So I modeled him from that point of view. But I also, and he said, he basically just character assassinated me. That was his point. That was his defense. He character assassinated me using his consensus base, and that's basically what he did. And he tried to say I was using dodgy camera heights, load of rubbish. But his other photograph, I modeled perfectly using the one where he had looking at a lighthouse with the horizon below the lighthouse. I modeled that perfectly for him on my kitchen floor here in the house, and I did it exactly to the millimeter. I had it perfect, right? He ignored it completely, and the Brazilian cameraman who came out against him, he tried to character assassinate him, and the guy Lewis pointed out that Miles Davis has another observation where the horizon is above the lighthouse, because as we know, when there's bad weather, the horizon will be closer and lower. When there's good weather, it'll be further and higher. That's what happens. Yeah, we know this, right? That's what the horizon does, because the horizon's not a real location. Now, sorry, Ranty, I just had to put that in. I've been waiting a long time to say that.
No worries. I did want to talk about this image, though. The one that you was just talking about, actually, the boats that appear to be on the horizon, and then there's a boat just beyond it that appears to be sort of like half sunken. You know, because this was pretty much, I remember it was a few of was it Wolfie that put this video out? I think it was. Or he has promoted it anyway. And if you get to watch it on the watch page, if you've got the watch page open, you'll get to see it. What will happen, it'll come through in a second. So what we have here is we have this boat, the Hunagayan Spirit, that's 9.9 nautical miles away, Energy Panther and the Overseas Yellowstone. But if you look at the Overseas Yellowstone, which is 7.7 nautical miles, that's pretty much on the horizon. Yeah. And then we have a boat that's just 2 miles beyond that, 2 nautical miles beyond that, that's half hidden. So 50 foot of this boat, 50 foot of this boat here is missing over just 2 miles, right? And that can't happen. It's impossible. On their model, it can't even happen. If this boat is floating on the horizon and this boat is floating on the horizon, this boat, which is just 2 miles further away, cannot be 50 foot hidden. It cannot possibly be that, but it can absolutely be that effect with shoaling, because these boats are probably riding the shoaling wave, you know, that area that's being lifted up, and this boat that's the 2 miles further away is he's not having that effect of that shoaling. It's not riding that wave that these ones are, and that's why it appears to be 50 foot hidden. Because I think over an extra 2 miles over that distance, there should be an extra 13 foot of refracted hidden or so. So essentially, it should just have been a smudge that was missing from this boat, but we've got like 50 foot of it missing here. You know, and it's absolutely provable that this shoaling effect is what's the cause of this boat losing at least half of its size. You know,
because the swell height is angular size is enough to cover over half the boat. That's about the size of it. The swell is high enough. It's not like the swell is rarely. If you take the rest of the ocean after the shoaling part, after the swell, the rest of the ocean will be undulations and whatever, but it's basically along the same level. But at shore level, because the ocean is moving in onto the shore and moving away, it's causing this shoaling effect. Yeah, because of the topography underneath the water. Do you know? It's so simple. Like, I mean, anyone with a logical mind would just go, oh well, that explains it. Do you know what I mean? Now it's not a mystery anymore. You know, it was explained as our curve as a mystery before. But now it's not a mystery. You know, now we know what it is. You know, this kind of thing. But you know, I actually was going to present this video or this photograph in, and Ranty knows this, in my last presentation, or the one before the last one. But because it was limited on time, I didn't do it. But I was going to say exactly the same thing, Ranty, because 2 miles away, how can this boat be? Like, they're big boats. Like, if you're standing next to them, even like as they're at their water level, if you stood in a small boat next to them, you'd be tiny, like. You know, you'd be tiny. The boat would be 60, 70 foot above you.
Well, I have an image on screen that sort of like demonstrates that. We have the shoaling zone, which is clearly where those two boats in the foreground were probably on this shoaling area, and then just 2 miles further, when they're away from this shoaling zone, obviously the water settles down again, so the boat will prospectively drop behind this shoaling zone and these boats that are sitting on it. It's so obvious now when we look into this.
Well, yeah, but
hello guys, by the way.
Hello.
Oh, hi Owen. You all right?
Yeah.
Salute, Owen.
I know. Gleam. I know you are a Glober. Yes, you're still a Glober. You're on the fence anyway, at least. Yeah.
Yeah, I'm agnostic. There we go.
Because sometimes I forget that when I'm speaking with you, because you're so open-minded. I forget that you're still maybe on the other half the other side or whatever. So don't take it personal if I'm.
I never would.
One other thing to take into account, I was thinking about there recently. Nobody's taking this into account. You know the way when someone gets an observation over water, and one day they can see further than the other. One day they're seeing a good distance, but the next day they can't. Because there seems to be water more in the way, blocking the bottoms of things. And I know there's kind of an argument about, like, there's different atmospheric effects and there's tides and this, that and everything, but there is another thing that will affect it, and nobody's taking this into account, and that is hydrogen bonding. Because if the water changes in temperature and goes to a lower temperature and starts getting into colder, the colder the water gets, then the denser the water gets. So then the hydrogen bonding, what happens? The hydrogen bonding naturally starts pushing apart the molecules. That's why ice, when water turns to ice, it actually that's why it takes up a bigger volume, because the hydrogen bonding has pushed the molecule. It's pushed the molecules apart. So it's colder. As water gets colder, it'll swell. You know, that's what it'll do, and people aren't taking that into account either. What would you say about that?
Are you sure about that? I thought that the only point at which water actually expands is exactly when it freezes, not just when it gets colder.
Well, but if you take a wooden gate, Arwen, like we have wooden gates at the back of our house.
Well, as far as I know, one of the most unique properties about water in the first place is that it is incompressible. So to assume that it would expand...
Yeah, but
based on temperature, I haven't seen that.
Yeah, but expansion is out the way. Compressing is in the way.
Yeah, but if you have hot water and you leave it to cool, it doesn't go down either. So I don't know where you're getting this one specifically
How
from.
does cold water have higher density than warm water then? Because warm water is heading more towards gas, and cold water is heading more towards ice. It's got to do with the hydrogen bonds.
No,
I disagree.
disagree with that.
No.
There may be a small differential in density in terms of liquid water, but the hydrogen bonding only comes into play when they become static in a crystalline lattice. So the hydrogen bonding is relevant to the orientation within the crystalline lattice. When there's still free moving particles as a liquid, then realistically the hydrogen bonding isn't, as far as I'm aware, overly relevant at that point. It's only a matter of alignment within the lattice. And because the hydrogen bonds repel, the electrons repel each other from the hydrogen and the free electrons on the oxygen, that alters the alignment, which causes the quirky nature of water to have a larger volume in its solid form.
Right. Oh, more dense, less dense, like why in tropical waters ships sink so much deeper than they do in the northern colder regions. On record, they have a special line on the ships for that. But that's compared to density of other materials, really.
Yeah, the plimsoll line is on ships, yes, because in colder water, ships can carry more weight because it's more dense than in tropical waters. They can't.
Right, but that's specifically the relation between other materials and the water, not water and water.
But it's the water.
You see, Brian.
Yeah.
Right. Obviously, when the water cools, it gets more dense. That's correct. So, ship-wise, load can be increased slightly, but it's the opposite. If you're going to invoke hydrogen bonding forces the molecules further apart than they would ordinarily be. So they're further apart. So it's less dense.
I don't think homogeneous liquids tend to do that typically.
But
I think that's only gases and non-homogeneous liquids.
I'm not speaking to
the
water though. I'm speaking to the swell. The point I'm making is, as the water gets colder, it's more likely to swell because water doesn't just become ice in a moment. It's a process. So it depends on how cold it is. Water will take time before it goes from liquid to ice. So from a liquid to a solid.
You mean because of because it's colder, there's less turbulence, so it won't be able to get away as much and heap up more. Is that what you're trying to say?
No, the point I'm making is that as it's getting colder, the more it's heading towards ice, then is that not causing the hydrogen to start pushing the molecules apart?
Yeah, but that's only truly at the freezing temperature. So. Yeah, the only example you can use that on is actual freezing ocean where there's ice.
Yeah, but water doesn't just become frozen all of a sudden.
Yes, it does.
Well, how fast does it go from water to ice then?
Very quickly, very suddenly. If the critical temperature is overlapped, then the crystallization process, actually almost like a chemical reaction, can just freeze up. You can have liquid very, very, very cold, yet not yet freezing, and then suddenly make it a little bit colder or introduce, for example, a little salt, lowering the freezing temperature. Or no, wait, that's the other way around. Some other substance, and it will suddenly flash freeze, while before it was all liquid.
Well, it's
very sudden.
Well, it's freezing at the moment where I am. I could pour water outside on the footpath, and that water won't go frozen for a while. Yeah, everything else is frozen, so it won't happen straight away. The point I was making.
But you're talking about sorry, but you're talking now about locations where the temperature is specifically below 0 Celsius. So that's not the conditions that the oceans are in.
About that, I'm talking about the process of water becoming colder and how the slightly colder water would make it swell. No. Well,
just no.
In the
water is incompressible.
In the winter time,
it doesn't do that.
1 second. In the winter time, right? In the winter time, when it rains, the wooden gates we have, right? They don't swell until it starts getting colder. If it's after being raining and into the wood. When it gets colder, then they start to swell. Now the water's not after becoming ice inside of them.
Yeah, but you're making a causation out of a correlation.
Well, it's not. Well, water does become ice.
Yeah, but it doesn't.
So
but before it becomes ice, it doesn't increase in volume. It just doesn't. Very simple.
So it doesn't swell beforehand.
Right. So you can only apply those types of conditions when it actually is freezing, which is not the case here.
Well, why did the wooden gates swell then? When it gets colder, if they're wet, and why it gets colder? If they're not freezing, if the water inside is not freezing, why do the gates swell?
I don't know. I think it's. I think you overshot. Can I please, as a final response? I think that what could be, if you're going to go with coldness, I think the only thing you can kind of attribute to shoaling being more promoted by cold is because water becomes less turbulent, less flexible, as proven when you drop ink stains in cold water versus when you drop it in warm water. So that way I could imagine that water in a cold condition would more easily heap up and not flow away. That's it.
I'm not talking about shoaling.
It's because of the turbulence, not because of any compression or expansion.
I'm just talking about in general why one day someone can get a different observation over water than the next, and the only difference might be the temperature of the water.
It may have some influence.
I could be wrong about it. I could be wrong, but I was pretty sure that water, as it gets colder, does start to swell.
I think
I don't know where you're getting that, but
yeah, I think Adam touched on it earlier, where he was saying it's only when it's in that particular structure, meaning the lattice, where it becomes a solid, does it then exhibit that swelling. Yep. I think
that's when it starts to crack stone.
Yeah, I was with you, and I was going to interrupt right early on and basically say I get it if you're talking about the vaporous percentage is more near the surface of the sea. Yeah. But then as soon as you said no, as soon as it's the actual coldness of the sea, I don't think it works like that, because it's still a liquid, it's still fluidous. And even when it becomes sort of like just before freezing point, it's not going to swell then. It's only until it becomes the ice will it then actually form that lattice and then start pushing everything out, because it's so dense.
Yeah, so technically temperature will have influence on the optics, but not on the obstruction. Because shoaling is not optics, it's obstruction, over amplified by perspective effect, which is just a side effect. But it isn't a visual.
I think the refraction's not the only thing in that picture though, Ranty. I think that it is perspective as well, because depending on your height, you can only see a certain distance to the future. That's where to the future, into the future. See,
into the future.
when you get these analysis eyes, but no, you can only see to a certain distance, and your false horizon, let's say, is created by this limit of your optical device. Or your height.
Well, the human and the boat are clearly in focus, so there can't be that much difference between the two.
That's a buoy.
Yeah, on this one, it's a similar thing. You can obviously see that there definitely is a wave just coming in, isn't there? Where there's a difference in the colouring of the actual ocean being flatter and a big wave. So you can see that there's definitely something hidden, and plus you've got refraction behind that. So
I'll give you an idea. It's in Hawaii.
Yeah, no, I've seen the actual analysis on this, and the video. It's a video, isn't it?
No. This was just an image that. What was he called? Who was it who did the analysis now? I can't remember now, right off the top of my head.
It's magnification, wasn't it? It was over the other side.
This guy here with this symbol down in the bottom.
Yeah, he was.
He did a presentation on my show. This is really bad, I can't remember his name. But anyway, it was just an image that he'd posted from some of his snaps in Hawaii. And as soon as I saw this, I was like, well, how can the boat be in focus, clearly no more than a couple of miles away, the human's in focus, and they are above the water. His feet are above the water, and yet the boat is half sunk. What's causing that effect?
So,
and like you say, there is a little ripple there, just between there and there, but the whole water itself is actually raised, and that's due to the shoaling that goes on around Hawaii.
Right, and shoaling will typically, because of the slight elevation, yet making a big difference because of what is further away, shoaling will typically then kind of set an extra horizon point even closer by and aggravate the optical slant effect, the deviation.
Exactly.
Because of the combination of the raising and everything else. Because just a little height makes so much difference as to where the horizon is going to appear in the view.
Randy, Blue Marble Science is in chat and he's calling us basically a crowd of idiots. Would you mind if I just share my screen again just to address him there on what he said earlier today on Jose's?
Yeah, sure. I mean, no, I don't. Has he got a channel, this Blue Marble guy?
Yeah, it's the.
Ah, tell me you know Blue Marble. Come on, he's the guy with the pipe, which isn't a container.
Oh, is that the guy? Right. Okay. Yeah, I wasn't even aware that he had a proper channel. I thought it was a lunatic actually putting that video out.
According to him, we're a crowd of idiots in the chat there. So I just wanted, if you don't mind, I'm just going to share and just show that olive jar again, if that's okay. Okay?
Yeah, you're sharing now, yeah. Go ahead.
I didn't want to go showing unless I made it totally okay. Okay, this is for you, Blue Marble Science. Today on Jose's, the bit I listened to, you claimed that you did not understand why you could see more things with a higher camera angle than a lower camera angle. Now, here is a jar of olives that's obviously bigger than a thing of pepper, okay? It's like paprika or something like that in the orange. Now, the olive jar is obviously bigger. Now, I'm going to show you that by changing the position of the jar of olives and changing my camera height.
Hold, Ranty. Right. Yeah, you didn't have him on present.
I did?
You do now.
Okay.
Or there's a huge delay on YouTube. That could be as well.
There is a delay.
Yes,
all right.
30 seconds.
They'll hear it anyway.
Anyway, continue. Sorry for the interruption.
It's for swearing.
No, you did the right thing, Aaron. The right thing. This is for Blue Marble Science, who's calling us a crowd of idiots. Basically, he's saying we're like a crowd of children or something. Listening to it says it's something like it's like listening to a crowd of children. That's what he said in the side chat. Today on Jose's, Blue Marble Science stated that he did not understand how just because camera height is lower, that we should see less stuff and stuff should disappear from the bottom on a flat Earth. Okay, he didn't understand how that could happen. Referencing the observation that was made of the two platforms, that has been the Black Swan observation, the talking point of the week. So here is a jar of olives on the left, I think a paprika on the right. The olives is obviously a bigger jar, takes up more space. You can see the floor, totally not normal, just a normal floor, no big curves or anything on it. Okay, now I'm going to just change my camera height and the position of the jar of olives. It looks like the jar of olives, the bottom of it has disappeared due to diffraction. The diffraction limit had caused the bottom of it to start disappearing, and it seems to be sinking into the floor. There it is, occultated. There it is again, sinking backwards down into the floor as if it's going over the curve. This is what you're talking about, Blue Marble Science. And you're calling me and the other people on this panel idiots. And you don't even understand this. Is that gone over the curve? Blue Marble Science, can you come in and answer that? Is that gone over the curve? Because I know it's not. I know because I can show everyone.
Yes, the table is curved. It's R-based flat.
It's R-based, yeah. I have an R-based house.
Oh, that
Everything
was you.
is R-based flat.
Yeah.
I thought you'd done a mic drop.
There you go, disappearing into the floor. But it's not disappearing. It's just the camera height. It's the fact that the olives are behind the paprika, and my camera height has changed. It's lower. You can see how close I am to the floor. I'm just between half an inch to an inch. And you can see the olives seem to have gone over the curve. But they didn't.
Yeah.
That's all right.
Oh, and now Rumpus is going to say, but you didn't, the table's not entirely flat, there's an evenness is calling an obstruction and blah, blah, blah. Remember that?
Ranty.
Yes,
Ranty.
yes.
That guy wasn't Life is Short, that Travis guy, was it? Because he was...
Travis, Travis's Life is Short, yeah.
Yeah, he was the one that done the analysis on disappearing. If you remember, he done the hallway, and then he separates up each degree in the hallway from your upper and your lower field.
Yeah.
And then he done his final experiment on that big 2-hour video. I don't know whether you watched it, but his final experiment was laying out golf balls all the way down the hall, but in a curve. And it literally had, right at the end, it must have been about an eighth of the ball missing at the bottom, and that had merged in with the reflective floor.
Right.
And it clearly shows disappearance from bottom up, and that's with no atmosphere. That's just basic perspective.
Have you seen what they called Sky Free's latest video today? They put out
Sky Free.
You probably Sky Free, the channel, yeah.
Oh no, I don't have TV.
You probably haven't, right? No, it's a channel, right? Don't worry, I'll put it on in a minute.
Sorry.
I just
not
wanted
a TV channel.
I thought you meant Sky as in Sky 1, Sky 2.
No, fantastic! You're gonna love this. When I show you this video, you're gonna go, oh. Anyway, in the meantime, can you just go over again one more time, Brian? Why? Very quickly, you don't draw it out, but could you just tell, if you look on the watch page, you'll see that I've got Miles Davis's observation up in a line, and his camera height is supposed to be 221 meters. Hope Town Monument is 210, and then he's going to use all these different mountains in the distance to say that this is a proof of globe. Yeah. So could you just sort of go through this very quickly?
Present screen again, Randy?
Yeah. Miles Davis has been living on this for the past year and a half. He thinks he has perfect proof.
Yeah, can I just, in the interim, just butt in? And Bri, were you known as Mr. Brian 22 or something?
I was, yeah. I changed my on Randy's advice. I changed my name.
Now, this is a very important thing, and it's so funny that I'm here now and this picture's come up, because I've just had Miles do 5 videos in a row, hit piece on me.
Yes.
Yeah. Now it's because a year ago he challenged me to show him how it works on a flat Earth. And I don't know if Ranty will remember this, but on Nathan's show, we all showed ages ago the side-on view, orthographic view, but with an apparent rising floor, so it looked like a triangle.
Yeah.
Yeah. Now, either way, Brian, me defending you and saying to Miles, basically, no, you haven't checked whether it doesn't work on a flat Earth model yet. You've done no mathematics, no calculations, no nothing on a flat Earth. You've just pretended that this matches your model, and therefore it proves everything else wrong, which is the nutcase. So I was saying, you can't tell him he's wrong because of this. And I drew it out, I hand drew it and everything, and then a year later I debunk him on something completely different, and he pulls this thing that I done defending you a year ago back up, and he starts getting all salty, and I'm chucking at him, look, still on this exact picture that you just had up there, Ranty, he's called me out and said, how do you represent this on the flat Earth? And I've said to him straight away, you are going to have some temperature inversions, because he goes over 2 massive bodies of water in the 137 miles to Benin. And literally he done 5 hit pieces saying he's Gleam's a fool, because I tripped him up on something else about Lawrence Krauss and gravity and whatnot.
What Brian's going to explain here is that he's only got Hope 2 Monument to line up to. And what he's explaining here is, well, I'm sure, just go ahead, Brian, explain what it is.
Basically, everyone on the globe side is taking observations, and they're measuring background objects off of foreground objects. And what they're not understanding is angular size change will happen. So we have blocks here, they're half-inch high blocks, they're exactly the same. The one in here in the background, in the middle here, is the same height, is the same size exactly and height as this one here. And the ones at the background there's 1, 2, 3, 4, 5 of them high in the background. Now what I did is I drew a straight line from the top of this one. My camera height is actually just over the top of this. I've zoomed to this. My camera height is just over a half an inch, and it's just over the top of this. And I've zoomed to this one, and I drew a straight line from the top of this one to the third one here at the bottom, okay? And the one here in the middle seems to be, you could nearly fit another one on top of it. But that's angular size change that has happened. That's what's happened there. It's just angular size change. It's not that it's that it's smaller or actually got smaller. It just appears to. So if you want to get a true line, right, you have to do this.
This is the killer bit. This is the killer bit.
If you can see, this is the bottoms. When I line up the bottoms of this of these blocks, of these two here, and the one at the back as best I can see it, and the same at the top, it just turns into an horizon. The top, it's just like if these two lines kept going, and I'll just show you. I just keep them going here, and I just show. Right, they start becoming that. Right, they're starting to meet. That's an horizon. That's what happens. Flat Earth. This is what happens. It's that to get a true line, you have to be able to line it up with more than one thing. At least two things. At least two things to get a true line. So there is a line, is a true line. If I was looking with a camera, I'd look in a straight line, and this line here at the top, I just highlighted. This line here would be the one I think is a straight line. But technically it's not. Technically a straight line is actually down this way. That's actually the straight line, this one here. The one that's at an angle, that's actually this technically straight line. And the problem is they're taking these observations, they're not taking angular size change into account at all, and they're not lining things up at more than one place. They just have one observation and one point that they're starting from, and they're not making an alignment with any other things within the observation of similar elevation. And they're calling it our curve then when something appears to have gotten smaller and with distance. But as you can see with this, just go back to this photograph, with this line here at the top, this yellow line, this looks like it's an exact straight line, but it's not technically a straight line, because to be a straight line it has to meet the top of this one because they're exactly the same size. Right, so this one at the top here is highlighted. It looks like a straight line, but it's not a straight line. And Samuel Rowbotham proved this in the Bedford levels test when he lined up the crosshairs on his telescope with the first two markers, because when he lined it up with the first one, all the other markers dropped below it, right, in the distance. And he said that if I line this up with the first two markers and the rest of them line up, then it's flat. If the rest of them start falling away, then there's a curvature and it's possibly a globe. And he knew that he knew what he was doing, and he knew it wasn't a globe. Right, so he knew what would happen to angular, so he knew angular size change. So when he lined up the first two markers, all the rest of them stayed aligned. That's what happened. So that's how in the end of the day he won. That's how he won that bet, or won that case, was simply down to he proved angular size change. But they're using angular size change. I'll unshare my screen again, Ranty, now if you want.
Okay.
They're using angular size change, and they're calling it. Curvature, and it's not curvature. It's just angular size change, and they're avoiding visual occultation and the diffraction limit. But angular size change is the one. If you're looking at the watch page, and Randy puts back up that other photograph, it's obvious that there's a massive angular size change after happening.
So. Okay, so we've buried Miles pretty much, and I'm sure if you want to low down a bit more about this in afterwards, Gleam, we can go through it again. But I'm sure you pretty much understand it anyway. But this is the Sky Free channel that I wanted to talk about. In case anybody hasn't subscribed, I highly recommend you go and find this channel. I will link it in the show notes, and I will put a link in a minute into the chat. So if you get a chance to go on and subscribe, watch their stuff. It's absolutely brilliant. I'm going to play a video that they put out today. Obviously, they've started to do a little more detail. So they've started to put the details of the weather, etc., etc. It's not really that important. But what is important is that on the other side of the lake, they place these 3 objects on the other side of this lake. Now, this lake is only 600 feet across, and the camera is set down on I think it's a yoga mat that rests on the water, and to the center of the lens, it's about 1.5 to 2 inches above the water. So it's a very narrow angle. But crucially, over that 600 feet, there should still be no earth curve between the object and these objects on the other shore. But more importantly as well is this boat that they have. Now, they have this boat with a little flag on it, and what you'll see this boat dancing its way across the lake. Here we go, let's get it up to that part here. So you might have to watch this on the watch page. So here's this boat. It's going to be dancing on the other across the lake with a flag on, and you will see it disappear, wait for it, into the inferior mirage. Not only that, but all the objects on the other side of the lake are already completely immersed in the inferior mirage, but you actually watch this boat disappear and get lost behind that inferior mirage. Now, bearing in mind that this boat to the top of the flag is 9.5 inches. Now, I've got all these details from the actual channel owner themselves, so they've told me this. But the entire boat up to the flag gets hidden behind this inferior mirage. It's absolutely fantastic. And what we see here with these little like mouth things on the boat, like shark boat, barracuda boat, the stuff that I've been putting out, this is a small scale replica of what happens in the real world, and it's absolutely fantastic. And they do this quite a lot. There's a few videos of this same thing, of this boat disappearing into that inferior mirage. Absolutely brilliant stuff. And there we go.
Yeah, I see it.
There we go. Now I'm just going to pause it, hopefully. There we go. So now we've just got the flag. The bottom of the flag is here. This is part of the inferior mirage, but that's the bottom of the flag. But I would say at least 4 inches is hidden. The entire boat is hidden. Everything is hidden behind that inferior mirage. Now, there should be no earth curve. It's game over. This is it. You can't get lower than 1.5 to 2 inches with your camera, and you certainly, over 600 feet, there is no earth curve. It's as simple as that. The only thing that's making this boat with the flag disappear from the bottom up is the inferior mirage. Everything that I've been saying for the past, year and a half? So absolutely crucial, really good stuff. Go and subscribe today. I'm going to put the link in the chat right now. But yeah, brilliant stuff. And you'll see that when they raise up in a moment, you'll see where the objects were on the other side of the lake, completely hidden behind that inferior mirage as well.
You know what's kind of strange is that we're after having to get down into the small things, using small things to prove our points, like this video and 1 foot observations, and the things like I'm doing there with showing the angular size change within a house and on a table and stuff like that. Like, we're having to do that to prove our points. And what's after happening is that I'm after hearing from the Globe side in recent times that they're looking for us to do more bigger observations from a higher elevation. That way there won't be the same argument about atmospheric effects and all this kind of stuff. But when we used to do that, they would then take it and ignore angular size change, ignore visual occultation, ignore the refraction limit, and just call it Earth curve. They want us to go back to a position where they can call it Earth curve. You know, and that's ridiculous. You know, I mean, we had to move away from doing these big observations and make things smaller, get closer to the ocean and closer to the floor, and do smaller observations. You know, to prove our points. You know, 1 foot observations, angular size change using small objects. What's going on there with the remote controlled boats over a little lake. You know, things like that. We had to actually do that to start proving a point. You know, but now they want us to go back to doing these big observations because they can't argue with these ones. You know, the 1 foot observation of the platforms, that's a nightmare for them, in fairness. Like, now, Globe, sorry, Now, Gleam, I know you're a Globe.
You are right.
a power time globe, or maybe. So as I said, don't take it personal. But the only way to say it would be to say it rather than trying to be PC about it. Just say it, that kind of way.
No, it's just like if the way how you speak to me like that is more if you can imagine someone who's an atheist listening to a Christian and a Muslim speaking and saying, "Look, sorry if I disrespect your no God, but God is real. We love God." And it isn't as bad as that. That's an extreme example, but have you seen the picture that I've just posted in the side chat there, Ranty?
I haven't yet. I haven't.
That is just one photograph which shows boats disappearing from bottom up perfectly, absolutely perfectly, with fog, nothing but fog.
Professor Phil Bell has said, "I have a special video coming." Don't worry, Brian, your special video is on the way. I don't know what that's going to be. I think it's something to do with using small pieces, something like I'm doing, and he's going to show how I'm wrong. But I don't see how you can show that I'm wrong. I'm not manipulating anything. It is what it is. It's just natural stuff that happens. It's an effect, natural effect of a visual effect. So I don't know, Phil, I really don't know how you're going to disprove that one.
Yeah, he said the same thing.
Check on that picture.
Yeah.
That's not really angle of.
No, that's fog.
It's just literally atmospheric.
Yeah. Now put it this way. I always say I cut it in half in Photoshop, and if you imagine not even seeing the boat there, you would see that normally as a clear horizon. And I always say to globe earthers, look, where's the horizon there? And it obviously clearly looks where that solid line ends. And in my eyes, that is much closer than what we're actually seeing. I think when there's a limit on the device or the eye, then everything beyond that will get hidden bottom up anyway, just due to the angle of you viewing. Similar to where the critical angle is, which is the reflection point, the very last 0.02 degrees before it gets completely flat.
Yeah, that's like one of those. It's a similar. It's not the same thing, but it's similar to those. I have those photographs there somewhere, where there's like a float boat.
Floating boat.
Yeah, boat. And it looks like the boat is floating, but it's not really floating. It's just.
It's exactly that, because the horizon is so far behind. Because you can just chuck it in Photoshop and change the contrast, and you'll be able to see the true horizon is well behind the actual floating boat. And that's because it's mirroring, and that's exactly it. Imagine that boat not being there, no reference object. Then you would think automatically that horizon is dropping, or rising, and it's to do with visibility. If you can actually see, if you squint your eyes on the right hand side there, if you're good enough, if your eyes are good enough, you can actually see where the horizon is, and it is just below your mouse, Ranty. If that is, yeah, that's it. So it's in line with sort of like the very top deck or above where the actual captain is.
The viewing platform is level exactly with that.
So it's that. So that's well behind it, but the fog is bringing it down and towards you.
So can I conclude from this that you would be in agreement with us flat earthers that say using a theodolite to aim at the horizon is a pointless exercise?
Yes and no, but yes. There is ones where they do have a reference object in the back, and I think it's something to do with Soundly. I think Jesse went out with Soundly, and he stood at that point where you can see a hotel dead in front of you, and he actually showed that there was X amount of degrees drop in perfectly horizontal, but that's perfectly horizontal measured by a one of them spirit level bubbles, and it was on a rocky side bit of the actual bridge. So I don't trust that, in as much as you can say that, you can assume that for the model, for the globe earth model, and say that horizon is dropping, but I don't even think that horizon is there. It's nowhere near the other side. It's halfway between you. so to say. And then anything beyond that point gets hidden from the bottom up because you can no longer see the actual surface because it's the final point based on your height. That is the core thing, all based on your height.
Chris Berry, we're joined by Chris Berry. Hello, just to do a quick mic check.
Hey, can you hear me?
Yeah.
What's going on?
Salute, Chris.
All good. You asked to join?
Hello.
Oh yeah, I had some time. I thought I'd join and see what was going on. I caught some of the show earlier, but that was maybe 45 minutes ago, and I had to go get some food for the kids. Just seeing what the topic was.
Perspective,
yeah.
2.0.
What you were saying, Gleam, there a while back about the horizons. We know that the horizon's not an actual location.
No.
But the thing about it is that an argument from the board side, and Wolfie was one of the people that really pushed this argument, was that there's an horizon drop from a high elevation, what they would call an horizon drop. Now, obviously, with good weather, the horizon will be further out and higher up in an observation. And with bad weather, it'll be closer and lower, right? Yeah. That's provable over and over again. But what people don't realise, and I said this to a couple of people, I don't know if I said it to Wolf. I think I said say it to Wolfie, but I'd say I'm surely did say it in some comment somewhere. I made a video, and I did because I shared this video with Wolfie a load of times, and I doubt he ever watched it, but I kept on sharing it. I made a video, it was only a 4-minute video called Horizons Day a couple of years ago, and people have to realise, if you go, let's say, 500 foot above the ocean, then the ocean is going to be the bottom of the horizon, let's just say. So you're 500 feet above that ocean, right? And if you go 30,000 feet above that ocean,
hey,
how are you going to keep the same? How are you going to not have to look down towards an horizon? Unless, because the distance you're seeing from an airplane, unless you got very good weather, the horizon is going to appear lower on the HUD, where you have the HUD
head-up display.
Head-up display, yeah. Like the horizon is going to appear lower on that because you're 30,000 feet above the water and the land.
Of course.
It's always going to be in accordance with how much higher you are above the water and land. That's
what angle should the horizon be on a flat Earth?
By the way, this is Ruhif, by the way, guys.
Hello. I was going to ask Branty why you didn't get why you got Chris Berry in but not me, and then you did. Nice one.
No worries.
But anyway, can I reply to that, Brian? Because it's like you're narrating my experience with the flat Earth versus globe Earth debate, where I too have had the exact same argument with Wolfie directly, and I've got a paper here that basically says that from above 1 mile, you can no longer see the hard horizon anyway. Because if you think further off in the distance, regardless of direction that you're looking in, there are clouds there, and you will never see the hard horizon from above the clouds. Now, it's actually a special paper on visually discerning the curve of the Earth. So the actual conclusion of the paper is that you can actually see it around about 20,000 miles, 15 to 20,000, foot, not miles.
Yeah.
15 to 20,000 foot. But
it would be pretty high, yeah.
but I get exactly what you're saying, and he has shown it. He has gone back. Fair play to him. He was always accused of the standard. You are pointing your nose up because you're showing a 3-degree dip, and there's a 3-degree nose up that you have to keep in order to keep flying.
That's irrelevant of the gyro on the plane, though.
Please.
Yeah, no, that's it. It's that he went back and he actually proved that he could fly straight on a perfectly straight 0, and still there was that dip. But I'm just saying the exact same thing as what we've just shown there with that half the horizon missing, the floating boat illusion. How do you know that white mist in the background isn't just more atmosphere covering up a further horizon? And that is the whole argument. The same thing with Walter Bisselin's calculator. He doesn't add any atmosphere or visibility limits to his, so the horizon looks well up at the top. Whereas on a flat Earth, obviously, that's what's hiding that further land.
But on a clear day, why is the horizon a crisp line?
But this, what, from above the clouds? No.
I'm talking normal.
Well, that was it. The argument was above the clouds, and that was the argument there. From down below, you can never actually record curvature from the surface of Earth. Put it that way. You can assume something is going over a curve if you're seeing it going over that flat horizon in front of you on the x-axis. Or should I say Z-axis, isn't it?
Ian Madison's asking me if I'm sober tonight. It's 11:38 a.m., champ.
Well, I would disagree with that, Gleam. As if it's a globe, then you should definitely be able to measure and prove the curvature and drop.
Yeah, I understand, but you got to understand from their point of view that there is a scaling issue. There is definitely a scaling issue, and you can always throw the old Neil deGrasse Tyson, you don't see curvature, but there's no mathematics behind that statement.
Well, he's saying that because he's covering his own back there, because he knows we're not finding curvature, and we're not going to be finding curvature. He knows this is not going to happen. So consequently, he's saying, you won't see it even from 120,000 feet. He's covering his own back there. It's like, because no one's going to be at 120,000 feet. Only the
he's wrong about that, by the way.
Sorry?
Neil deGrasse Tyson is wrong that you cannot see curvature from 120,000 feet.
I'm telling.
I've been
okay.
Yet to see it.
So Ruhif, on screen we have Quantum Eraser's Black Swan image.
Where? I can't see your screen. Hold on.
It's on Skype? On the watch page, if you've got it open.
All right.
Is that QE's image? The rigs? Is the rigs?
That's the rigs with the horizon beyond the second rig. Because you asked about where the horizon should be on a flat plane, and I would just say it's all down to the optics of the day. I mean, you can't. Yes. That's essentially it. Whereas you have a defined horizon, and this image kind of like goes against that defined horizon, wouldn't you say?
Do I think there are strong refraction events happening here today? Yes. And I showed you images from another one of these BMLSB 69's videos this morning, showing the difference between strong refraction and a normal day.
Strong refraction? You mean terrestrial R-based refraction?
Okay,
so you presume it is depending on the curve?
So
that kind of refraction?
What makes you think there's strong refraction going on in this image, though?
In this image, okay. So the FAR oil rig, whatever it's called, Grace or something.
Yeah.
So you've got the large rectangle. This is hard to do unless I can point to it.
It's blatant, really.
What's blatant?
It's blatant that you can see refraction. All the metal's bent.
Oh yeah, obviously. I mean that grain on the left is curved to the shithouse, right?
What
obviously.
You mean this? This.
I've got to wait 20 seconds to see your point.
The arm on the left. The arm on the left that's all bent.
That's
and warped.
Obviously refracted, right? Obviously towered.
Well, it might be refracted, but is there a reason why that's refracted rather than it just being terrestrial refraction? Could it not be?
What distinction are you trying to make with terrestrial refraction?
Well, could it not be Fermat's principle that there's something else going on rather than looming?
Fermat's principle, Snell's law of refraction, it's all the same. Like what distinction are you trying to make?
Well, there's obviously something going on in this particular location. Can you think what that could be?
Yes. Very strong refraction, yes.
Right.
And you can see it yourself, right?
Do you think there's a cause for that?
You mean the wobbly thing? You mean the whole wobbly... that is actual refraction. That's not the R-based refraction that you think refraction's supposed to be.
Yeah,
that's actual refraction.
This image is taken from 1 foot
isn't the horizon?
Right?
You realise...
Is that how way up on the...
Hang on, guys. Let me finish this. You realise this is a flare boom, don't you? It's for
which one?
This arm on the left. It's the flare boom.
Oh, okay.
It's for venting. It's for venting the burning gases.
Okay.
Right, and the hot gases, that arm, that's this particular part of the actual oil rig itself is going to be very hot.
Sure.
And
it's not going to be hot for like 10 miles, straight through that distance, right?
That's what's giving this warp.
I completely disagree.
No, that's what's giving this warp.
Yeah,
that's a very good reason. That's a very good reason.
If you get close to that, it will become straight. You're telling me that heat is radiating 10 miles? That's bullshit, Ranty.
You only...
It's bullshit, right.
Okay, no, that's very hot. There's a lot of gases coming out of it in and around that location.
Yeah, but if you get close to it, is it going to bend like that?
If you get close to
this is just a bit of Fermat's principle. That's it.
No, it's simply over distance.
It's not going to be bent.
Yeah.
No, bending.
That's
the curving
heat,
there is
light bending.
Distance, right?
It's heat, light bending, and it typically happens over distance. It even happens when you look over a road. Okay.
If you get close to it, it's not going to bend.
Fermat's principle.
That curvature you see in that, whatever you called it.
Why is the horizon bent?
Hang on, wait a minute. Fermat's principle is a deviation from straight. A deviation from straight over different gradients. So here we have a different gradient because this is very hot. And that's why we're getting this distortion on this boom arm. That's it.
It's not, because if you get close to it, it's not going to be bent.
You only see it at a distance. You're not
Ruhif, please. You need to go and understand Fermat's principle to understand what's happening here.
I do understand Fermat's principle.
Ruhif, could I ask you a question? Just from
you may. Is this Adam?
Evening.
Yeah.
It's Adam.
Hello.
Mate. How you doing? It was just a quick. You described it as extreme refraction there, and I just wonder why. I mean, I can obviously see it's wibbly wobbly. There's no, you couldn't make steel. You can see that it's basically curving, isn't it, away, and so there's no rigidity to whatever that steel structure is. But you described that as extreme, and realistically, in the picture, we're talking about a disalignment of pixels here and there, a foot here, a foot there, in real terms, in terms of what we think we're seeing. Now you're describing that as extreme, but
yes,
the reality is that the standard 7/6 refraction that manages to bring it all back into perfect clarity and perspective with none of this is not extreme. I just wondered if you could just differentiate why you consider that extreme, but in reality none of that's there. It's 70-80 foot below that. It's lower. So could you just differentiate why you think that's extreme? I'm not getting onto your standard boiler point. I'm asking why you think that's extreme and what's the causation of the extremity as opposed to...
Yeah, okay. The causation, what causes extreme refraction is an extreme density gradient, right? So you can actually see in this image, and this is going to be hard to do without me pointing to the screen. So on the left oil rig, you've got the big rectangular thing on the right of that rig. Below that, you have the two legs going into the water. Okay. There is a beam going from the. So this is under the platform. There is a beam going from the top right to the second leg. So the second leg from the right. Again, very difficult to do this without pointing. The horizon intersects with that beam. Okay. Can everyone see what I'm looking at?
Yeah, I'll show it on screen for everybody to see, but we know where the horizon intersects
if you can point to it.
Yeah.
Yeah, so the horizon intersects that beam. That beam, on the platform, yeah. So going from the bottom of the platform to the second leg from the right.
Yeah, behind the
where it intersects that beam is way more than 1 foot above the surface, like maybe 20 feet above the surface. Right, so your observer height here is 1 foot. So your observer going from 1 foot to 20 foot and seeing the horizon at that level, like, are you guys now concave earthers?
Hang on, wait a minute. We're not seeing it rise. Listen, it's not, just a minute, it's not rising up. It's just further in the distance, giving the illusion that it's lifted up. It's not physically climbing up the actual oil rig. It's just the perspective view as you're looking at it.
Your line of sight is going up, Ranty. Do you deny that?
It's just
on a flat Earth, your line of sight is going up.
Yeah, and that's exactly what's happening.
No.
You're looking.
What the hell are you talking about? Your line of sight is going up.
Yeah,
is the horizon above your eye level?
What?
No, Ruhif, what's going on here now?
No, you're turning things around. On a globe, you're supposed to be looking down.
Concave Earth,
yet that doesn't happen. We don't look up. We look straight forward.
The horizon is center frame. I think the issue with this particular picture is that your horizon, your fixed edge, should be some 5 miles in front of the first platform, making that horizon that we see merely holographic at best. Would you agree that if we are 1 foot above the ground, then when we're talking of the horizon, that hard edge at 1 foot, then like I say, your horizon needs to be 5 miles in front of that first platform, and therefore necessitating that everything else we see from 5 miles in front of it is holographic. It's not there.
It's not a hologram.
It's brought up. It's brought up, and where we see it isn't where it actually is, including the horizon.
Ruhif, 1 second.
Yeah.
1 second.
What about railway tracks? If you look down railway tracks, do they rise up?
They will appear to converge.
1 second.
Do they rise up though?
Ruhif.
What do you mean rise up?
If you're claiming refraction, right, has took your hard horizon from 1.22 miles away and sent it back to 10 miles away, and you're saying refraction has caused this, then that would mean a blanket uniform refraction, right? Not only is that impossible, right? There's no possibility of moving on a horizon, because what you're basically inferring is looming, which has to happen over and behind an horizon. But the horizon here is 10 miles away, not 1.22 miles. You need a hard horizon at 1.22 miles. And even if
that's not a refracted horizon, that's just your geometric horizon.
There's
no atmosphere.
So the refracted is 1.3. Hang on, wait a minute. Let's just clarify this. The refracted is 1.3.
Standard refraction 1.3. Yes.
Yeah. So what refraction is this?
That's based on a radius.
This is 700%.
You dickheads can quote me, right? You guys, you fuckwits can quote me on this. This is greater than infinite refraction.
So the infinite
refraction?
Infinite over 6R. Infinite over 6R. Quote me on that.
No such thing.
It sounds really, really profound, Ruhif. Would you clarify?
It sounds profound.
The point I'm trying to make, Ruhif, is that even if the horizon was at 1.22 miles here, and we saw these, and you were saying that these platforms were being loomed up, the problem with that is there isn't uniform effects going on across that whole observation, as there's completely different effects on the left than there is on the right. There's completely different effects on the left than there is on the right. So both ways your argument is taken down. You don't have the hard horizon that is impossible not to be there if we were on a globe. You don't have that. And you don't have uniform effects across the observation. So you don't have an argument. I don't see
My question is, if this observation is made at 1 foot, are you looking up or down to that little crossbar that we identified before, if it's at 20 feet? Are you looking up, above eye level, or below eye level?
But we're not looking up at anything.
It's not a fucking difficult question, Brian.
We're not looking up anywhere. There's no looking up. The horizon is stretching.
This is ridiculous.
The horizon is stretching out past.
What does the horizon rise to?
Hang on. It's not. The horizon is
eye level, straight forward.
Yeah, the horizon.
Eye level, not down.
That's all it is, Ruhif. The horizon is stretching out past the platform. That's all that's going on there. Where is that?
Are you looking? Rancy, this is soundbite time.
It's not there. You don't have
infinite over 6. Infinite. Who wants me to explain infinite over 6R?
I don't need to.
No, go ahead. I would
show me any kind of theory that has infinite in it and that is viable, hypothesis based. Okay, there is no infinite.
Well, I'd like to hear his explanation of it, though. That would be.
Can you distinguish between a sphere with an infinite radius,
1 second,
as opposed to a flat Earth?
1 second. It's been claimed that this horizon is lifting up. It's not lifting up. That's perspective, because
It's
what
not
happens is you're
perspective,
looking
it's
straight
refraction.
across the water from a 1 foot observation. So consequently, because there's good conditions, clear conditions here, it appears that the horizon is lifting up. Just like if you have bad weather conditions, the horizon will appear to be closer and lower down. If you've got good weather conditions, it'll be further and higher up, right? Because it's not an actual location. It's not a real.
Can you answer the simple question? Are you looking up to that crossbeam or not?
Sorry?
No.
It's higher than you. Why not? It's higher than you.
We're not looking in orthographic view. It's in the far distance. There's
This is a perspective view.
So
Are you
you're
looking
not
up to it or
looking
down
up.
to it?
The amount you're looking up is minute. It is
Yeah, but it's
insignificant.
up, right?
You're
It's up.
practically
Is it
looking
up
straight
or down?
forward because it's in the
Is it
distance.
up or
It's not
down?
up.
You need to concentrate.
Is it up or
Hang
down?
on,
No.
one
No,
at a
it's not
time,
up.
one at a time, one at a time, please, one at a time.
You need
This is
to
a very
concentrate
simple
on
question.
the horizon you're
Ryan,
supposed
Something is higher
Okay,
than
hang
you.
on,
Look
one
up
at a
to
time.
it.
Whoa. Guys,
to-
can I get Ruhif to ask his question, please? He's been trying for 2 minutes.
If you are at 1 foot elevation and something on a flat plane, we're assuming a flat plane, if you're at 1 foot elevation and you are looking at something that is, say, 20 feet above the water, are you looking up?
No.
If it's 20 feet above
Oh, who
water,
said no? Was that Owen?
Yeah, that was
if it's
me.
20 feet
You're
above,
fucking kidding me.
Yes,
No.
you are.
No,
yes,
you're
you
not.
must be.
you have to
No,
look
you're
up
not.
something if it's 19 feet above you.
No, you're not. The angle, because of the distance, is so
positive,
far that you're
If you have to
practically
look
not
up.
looking up. The amount you're looking up is insignificant because
is
it's
up,
very
right?
far
It's up.
away.
The object's at a
Is it up?
The
distance,
trick
you won't
question.
have to
The
look.
answer is
It's
no.
not a trick question. Yeah.
Yeah.
No, it is a trick question.
Yeah,
The
but you
answer is
didn't add
no.
in distance. You didn't add in distance, Ruhif, did you?
No,
You
he
didn't
is
add in
assuming
any distance.
orthographic view.
Oh,
Okay,
I'm not
that's
assuming
there.
anything else.
That's where
It's
the
a very
height
simple
is always
question.
the height.
Platform on the
But we're
right.
talking about something in the distance, so
Yeah.
a perspective comes into play,
It's
and
This is a
therefore
very
the angle of
angle
sight allows it.
where you're looking at
Hang
is going to
on,
be
one at a time, please.
straightforward.
One at a time, please.
Can I jump in just
Yeah.
real quick? Okay.
Yes, go ahead, yeah.
Okay. What I'm hearing right now is talking past each other. When that's going on, we got to stop and qualify. So I agree with Arwen's analysis, right? I agree, but I also agree with Gleam. Okay, so what, Ruhif, you're asking us to describe what we think if we have a viewer height at 1 foot and we're looking at something 20 feet above us, elevation. Okay, how close are we to that observation? That is going to be more helpful for us. How close are we?
Is it going to be above 0 or below 0 or exactly 0?
How
That's a
close
very
are we
simple
to
question.
the observation that you want us to make, Ruhif?
Well, say it again.
Ruhif.
What is my distance to the observation that you are asking me to tell you whether or not I'm looking up?
Like 10 miles or something. Isn't it?
Okay, then no, I'm not looking up.
Yes, you are.
Yeah.
You're looking up on a flat
No,
plane.
you're not.
How are you not? You can
No,
calculate
you're
the
not.
angle.
Because it is so small because of perspective.
Yeah, is it small positive or small
You're
negative?
Geometrically,
practically looking
yes.
straight forward.
Geometrically, yes.
You're looking
Thank you.
at the horizon. And without
No.
video assistance, you
You're
can't
looking at
even
this
see it. Yet you
crossbar.
can
It's
see the
19
horizon, which
feet
is
above you.
exactly in front of you. You can't let other people explain things, can you?
Okay,
Because it's
Ruhif,
such a
see-
simple
1
question.
second,
Yeah,
Arwen.
yeah. And I answered it. And when I
You said
then
it's very
explain it,
small.
you start over talking like a rumpus.
Ruhif,
Because
see
you
this-
don't want to hear the answer. You
You-
don't want to hear somebody actually saying no and then explaining it. You don't want to hear that.
Ruhif, see this thing in the center floating on the water. We don't know if it's a boat or what it is. See the little thing in between the two platforms. You know that thing?
Yep.
Are you looking up to see that? Because that's definitely more than a foot high.
On a flat plane,
Are you looking up to see that?
probably on a flat plane it would be.
Become small enough to be seen. Without
On a
having
flat
to-
plane, I'd be looking up to that, yes.
But you're not looking up to it there. You're looking straight across.
No, because the Earth's a globe. Thanks.
Are you looking up? Are you looking up to see it there? No, you'd be looking down at it on a globe.
Well, no, you wouldn't
On
see
a
if
globe,
it was.
yes.
On
See it all
you
on the
wouldn't
globe.
see it if
You
she was
all-
on a globe.
What you need to
Well,
do
it depends on the
is for a horizon that should be at 1.22 miles and stop messing around with the minutiae of nonsense that you're trying to do.
That's the geometric
That's all
horizon.
you're doing. Oh, the horizon is this. It's over there. There's a bit of refraction over here. Where's the hard horizon, Ruhif? It's not there.
There's not, because it's such a long distance away, because refraction has reached a point where it's in line with the curvature of the Earth.
To do with it, for refraction to do what you're talking about, you're inferring looming, and you're talking about standard refraction.
Oh, let's get on to looming. I sent some photos to Reggie this morning.
Looming is only possible, right, on and past an horizon, not before.
Okay, well, before we wrap this...
Actually, Ranty, can you show those photos I sent you this morning?
Well, before I get to that, just before we wrap this up, your only explanation for this image is infinite... Can you say it again, exactly what it was?
Infinite over 6R refraction.
Infinite 7
to
over 6R
to the point where it might even be concave. It might even be concave, which is actually
How come that's not uniform across the observation group?
Because the density gradient varies. You can see that in the gas flare thing. It's obviously all over the place, right?
But the density gradients are going to be the same. I mean, as you when you go higher, there's a different densities in the atmosphere. Yeah, that's true. As you go higher, but the density is going to be
density gradient.
How come there's more? How come the platform on the left is a lot more affected by atmospheric effects than the one on the right? Because what you're saying involves a uniform effect. But you're
it's clearly not uniform. It's clearly not uniform. What you're seeing in the curvature here...
What you're saying, and what you're saying is nonsense.
No. I can back all this shit up. I can back all this shit up.
You can back up infinite over 6R?
Yes, easily.
Where's that at?
All it means is the density gradient is the same as the curvature of the Earth. That's all infinite over 6R is.
Yeah, where's the documentation?
Right, but that's just... Yeah, but you're just describing something. Show us what infinite over 6 hour looks like, please.
It looks like a flat plane. That's exactly what it is. Can you distinguish?
So your fictional formula that has infinity in it, and that nothing that has infinite in it has any empirical basis in reality. Okay.
Yes.
So that's actually your fictional creation using something that's excluded in actual physics and science. This is infinity is excluded specifically. You're going to use that to say, that makes it look exactly like it is, perfectly flat.
Right.
It's just
when the density gradient reaches a point, can you distinguish between a sphere with a radius of 1,000,000 kilometers? Can you distinguish the difference between that and a flat plane?
No.
Well, the first
You're saying it is a
very good. Who said no? Who said no?
I said
Who said no? Very good.
But essentially,
can you distinguish between a radius of 20 trillion squintillion kilometers and a flat plane?
We can distinguish between all that and the presupposed sphere Earth that you believe in.
Hold on, guys. What we have right now is another category now of the great scale negator, right? That's my term, the great scale negator. We know that we're spinning because we can't feel the spin. Okay, so now what Ruhiv has just said is, it's a globe because it looks flat.
Yeah.
No, in this particular photo, it does look flat because the horizon is actually above
eye level. Can I share my screen, Ranty, if you don't mind?
Ryan Q. Vincent, come in, champ. Come on. Actually, we're going to have an after show, or are you going to kill this now?
No, I'm going to carry on until you guys are tired.
Cool. All right, I will go until my doorbell rings.
I was up until 6 yesterday, so there's 4 more hours for me.
Excellent. All right, I've got an aircon repairman guy coming shortly, but soon.
What I think should be noted is that the actual horizon, I don't know whether it's been cropped, but if he's got that horizon perfectly like that, he's actually as level as he should be, put it that way.
I don't know what that means.
If the horizon is dead center, then he is dead center of the vision, of the view to the horizon.
The center of frame is pretty meaningless.
Can I share my screen, Ranty, a second?
Yeah, fire away.
1 second now. I'm just going to refer Rupert back to something. And we'll go back to this observation then. Okay, something I showed you earlier. Rupert, do you remember commenting on this video? Do you remember commenting? Wait till you see. Can you see that in your...
I've got to expand my screen though. How to do that? There we go. Yeah, go, yeah.
Do you remember commenting on this video? My YouTube name was slightly different. It was about 2 years ago.
Mr. Brian 22. I don't know, maybe a year ago, something like that. Yeah.
Yeah, something like that. Maybe a bit over that. Now, you said your explanation for this, because this is Mount St. Helens in front of us, and this is Mount Rainier at the back. Yep. And I told you that I couldn't get my camera height any lower, because if I could get it lower, then that would occult Mount Rainier at the back more, and you would see less of the part that's sticking up here over the left of the Mount St. Helens piece. Now, the reason I couldn't is I couldn't get my camera height any lower than that. Now, your only argument here was, how do I know I have a flat floor? Even though you can see the bottom of the block here at the background. This is totally to scale. The only thing I don't have to scale here with the Mount St. Helens photograph is...
If it's totally to scale, why don't you just do it mathematically?
No, I scaled it.
Yeah, but why don't you just do it mathematically if it's to scale? Why go to the trouble of building a little block that's, could be a couple of millimeters out, which might translate to, I don't know, a couple of 100 feet.
No, well, the idea was to show that that was absolutely possible on a flat Earth. And if I could have got my camera height lower to the actual height that was the same as the photographer had, photographer's elevation in accordance with Mount St. Helens, then the Mount Rainier would be even more occulted, because I'd be looking up at more of an angle to it.
Sure.
Right?
Yeah.
Right. Now, your argument there was that, how do you know your floor is flat? My floor doesn't have a radius. So
yeah, but it might be dipped.
That was your argument that video was. So how can we trust, if that's what you're going to say, even though we can see the bottom of the blocks here?
We can trust. We can trust a mathematically straight line.
Ranty, you can't see this on YouTube. I don't know if you care or not, but...
Sorry, it should have been on YouTube.
Well, that's weird, because I can see it on my YouTube screen.
Oh, I'm sorry. Okay, I'm not live. My bad.
Yeah, no worries.
Oh, same, actually.
Yeah, I can see it.
There we go. I'll turn off
the live stream. A second.
Can I do one after him? I gotta go, but...
I want Ranty to show the looming. Show those photos I sent you this morning, Ranty.
Yeah. 1 sec.
But in short, to Brian, mathematically you'll get 100% accuracy. If you do a physical model, you're leaving the door open to making slight mistakes in your scale.
No, there's no mistakes in my scale, Ruhif.
You're not a millimeter off on your.
Well, I was. The only bit I am off.
Okay,
My camera height should be lower, but I've already stated that and stated it in the video. At the end of the day, it's a flat floor. I modelled the photograph that you say.
You sure your floor's not like a millimeter off flat?
Possible on a flat Earth, and I modelled it like I modelled all these other photographs that are supposed to be impossible on a flat Earth.
Right. So how have you shown that your floor is not flat down to the millimeter?
Excuse me, but how is that millimeter going to matter?
What's flat or not?
Well, if you scale it down, a millimeter, I don't know what your scale was, but that could be 100 feet.
So you're saying that there's obstruction after 100 feet? The curve is that close?
No, I'm saying his scale. If he's making a physical scale and doing it like, I don't know, 5,000, 10,000 to 1 or whatever, then a millimeter makes a difference, right?
But I'm not. But the problem is, Ruhif, that you're looking for very small things to try and avoid the fact that the floor is flat.
Because they make a huge difference.
You and others said that was impossible on a flat Earth, and I showed it being able to be scaled down on a kitchen floor. In the end of the
physical model that has imperfections on it. Do it mathematically, and you won't have the imperfections.
There's no compression going on. There's no atmospheric effects going on there. So the point I was making is, how can anything you say be trusted when you're going to say silly nonsense like you're saying, like whether my floor is flat or not type stuff? How can anything you're going to say about anything after that? Because it's obvious the floor is flat, because you can see the bottom.
It's not obvious the floor is flat.
I called it though. I said this would happen, but instead of Rumpus, it became Ruhif. Called it half an hour ago.
So the floor is not flat.
I called it.
You haven't demonstrated that your floor is flat to the scale that you need it to be flat.
Well, it's as flat as the Earth is flat.
Oh, well, I'll take your word for it then.
Yeah, well, it certainly doesn't have a radius.
It's flat enough. It's not curved. It's not.
Is it flat enough? You haven't demonstrated
this.
Yeah, flat enough.
Here we go.
Okay, so let's I've got this image up now that you sent me today. Obviously, we have two completely different weather conditions. We have a very choppy day on the left, and we have a pretty flat water on the right. But there's these black lines. I hate seeing these black lines in it. I just have to say that. So I'm sorry about this, the audience, but this is what Ruhif has presented. But I can see what you're trying to say. I can see what you're trying to show.
I can't see it on Skype, by the way.
Can you see it on the watch page? It's on the watch page.
Hold on.
I can tell you straight away, there are two different crop factors there.
Okay. Mute. All right, what was that?
So we have two completely different weather conditions. It appears to be the same objects that we're looking at, different zooms for sure. But what's your take on this then?
Right, they're from the same elevation. He actually says that on screen like a few seconds before this. I would
have to disagree with that, and I'll tell you for why.
From the same elevation, you're calling a liar.
Yeah, but
you're calling your own flat earther a liar.
I don't know if he's a flat earther or not, but I'll just tell you. Well, firstly, I just want to say that I can tell you the one on the left was taken from lower than the one on the right. And that's simply because, and I can tell that immediately because these two on the right, the building on the right with the square tower and the little ball, they're completely level. And then when you look at the square tower on the left-hand image and the ball is lower than the square tower, showing that he was actually at a lower elevation.
So just to be clear, you are saying that the relative heights of those platforms are different, and therefore he was at a lower elevation.
No, I'm saying that he was at a different elevation when he took this first image on the left.
Yeah, so you are accusing me of lying, right?
I'm just saying that I can see that there's a discrepancy. Well, I'm just saying I can see a discrepancy in the image immediately, and I can see that it's lower than what he. You know, if you're going to tell me that these were taken at the same elevation, I would have to disagree.
Can I respond to that?
And if he says
to that real quick, please, Rufus?
Yep, go.
Okay, this seems to be the same critique that Sean G and Erebus leveled against me with my Chesapeake Bay image, because I was telling them that I'm set up at the same place with the same camera height and the same distance, and they were saying that's impossible because what we're seeing doesn't match up. And what I'm suggesting is that is the dynamic mess with your mind Aether band effect. Okay, what you're seeing.
That was just fucking word salad.
He's correct. He is correct.
Thank you. Let me just finish real quickly. What you're seeing is a distortion of the same distance, same field of view that has been distorted by the conditions of the air. So,
I agree. It's caused by the conditions of the air. 100%.
So what I'm trying to say, though, to Ranty is, I would say, because I've been critiqued in the same way, Ranty, where I have been called a liar, that I'm not at the same location. I am at the same location. Well, then why do you have a different field of view? Because the effects of the conditions have changed that appearance.
I don't know what conversation you had with Sean G.
Zone.
I don't even know who I'm talking to be honest. But this, Ranty, you're saying they must be at different elevations? Is that what you're saying?
It would appear so, yeah. I mean, you can even see...
So you are calling him a liar.
Well, to be honest, and, you know...
Oh, there goes my doorbell. I'll try and be back in a minute. Hold on. I'll be back shortly.
For the audience, for the audience's point of view, if you look at the left-hand image, the platform that's on the right-hand side, the smaller one, is level with the centre, I would say, of the big oil rig on the left. Whereas if you look on the image on the right, it's almost at the same elevation. And that can only prove one thing, that they were taken from two different elevations. You wouldn't get that parallax.
But Ranty, to Travis's point, that's not necessarily true because, first of all, the dimensions in both images, the platform on the right, the dimensions are off. Like the one on the right is more square and the one on the left is more rectangular, right? So we know the atmosphere is at play. And what Rufus is going to come back and say, well, why is the one on the left, why can't you see it, the bottom of the one in the back? Well, our only answer can be refraction. It's not Earth curve, right? It's refraction or it's angle or distance or whatever.
Isn't that just sinking?
Exactly. It's just refraction. It's refractive sinking.
And the other one seems like towering. It's stretched up.
Or that's what it actually looks like, right? I don't know what the thing actually looks like. I mean, they're on platforms.
They're the same thing, right? So the one over the right seems like it's stretched up. So that's towering. I think.
Right. But I think this, like I say, I mean, that's my opinion that they're taken from two different elevations. But I think ultimately it's to get away from this image, the black swan, and I think that's what this diversion is.
Hey, Randy, I'm sorry.
No, it's fine. It's fine. And Quantum Eraser is quite correct. He says you only need one black swan, where the weather conditions are just perfect. In which case, they're going to come back with infinite refraction 7/6R.
Correct. Hey, Randy, I gotta go. Can I just show my video real quick?
Yeah.
It's a little off topic, but it's also a little on topic. So
are you presenting your screen? You mean you're not going to play a video, are you?
Oh, yeah.
It's not got music in it, has it? Because every time you play a video with music in it, I get a copyright strike.
Every time I have returned a video with music in it.
Yeah, you've done it twice to me in the past. Every time you've joined, you played a video with music on, and I've got a copyright strike on my channel.
I don't think it was me. The only music I put in my videos is my own music.
Okay, well, let's have a look.
This is my video.
Okay. Well,
can we go back to the looming shortly?
Yeah, sure.
I don't know how to screen share.
Cool.
Hey,
I have to
Randy,
go at 12:30. So. Yeah.
Randy, if I may say something about the two rigs, comparing two photos.
Share your screen.
I don't see any. I don't know how. I don't see any button.
The two squares that are overlapping each other.
I don't have that. I think it's because you're sharing still. If you unshare,
I'm not sharing.
You're not sharing.
You just have to click.
Oh wait. Oh, hold on. Okay. Apparently, if you have the chat open, you don't see those two squares. I don't know.
If you can't, it's fine. We'll put it on another time. So I'll link people into it though.
Randy, I just wanted to say for a second that I think you're right, because remembering from what I saw now from comparing two pictures of those rigs, the one on the right, the angles were slightly different. So it looked like that one was taken from higher up, because the shape of the rig was slightly off. In the one to the left, it seemed perfectly parallel. On the one to the right, it seems somewhat diagonal, slightly. So
rotated. Yeah.
He doesn't have to be a liar. He might just be wrong.
Yeah, he might have.
For him to explicitly say in his video, different day, same exact location, same exact elevation.
Can you see my screen?
Yes. I can't tell. Yeah. Well, we'll get back to that in a moment. I'm just going to play this out.
I only got 10 minutes already, so.
Yeah. Okay.
Yeah, I'll play this and I have to go. So, So basically, on Jose's today, they were talking about angle of attack and all that. So I wanted to show something a little different, but still dealing with angle and limited visibility and things. So what I did, I took a 5x7 car stock photo, and I drew a red, maybe three quarters of an inch to an inch red line, and then I'll just start playing it. As you can see, I put it towards the end of the counter in my kitchen, and took this level, and I leveled it out across about 6 or 7 points, just to show you that it was, I mean, this is basically as a near level of a counter as you can get, granite countertop. So I do this, like I said, 6 or 7 points of level. So there's absolutely no possibility of a claim that there's any type of physical obstruction due to the counter. Assuming unless the ballers will then come back and say, well, your level is off, right? There's always a one extra step. So anyways, let me, I'll just fast forward a little bit.
Okay.
So what I do is I zoom in I'm using an iPhone. I zoom in. I'm about three feet above the counter. Okay. So let me just pause it here. So obviously you can still see that stretch of red in the white card. Now the question is, what happens if you lower the camera? Now we all know that the answer, ballers will say something else because they're stupid.
No,
but we know that.
I'm going to agree with you, Chris.
Yeah. It's going to be obscured, right? So the question, if I'm Brenda, I'm like, where did the red go, Ranty? Where did the red go, right? So not only do we know for a fact, if you didn't already know, right, I'm just proving the point that height changes the angle, which changes what you can see. I then bring that same, so now it's the same height. I bring that same card forward, and by simply changing the distance, also changes the amount that you can see of an object. So now you'll see the white, and now you'll see the red coming back into frame as well. So,
and your point is what?
The point is that change of angle is can be both caused by height and by distance. And if you apply both, like if you have many miles in your low observation, your angle is going to be drastically changed. The second
Not to
is
an object that's perpendicular to your vision. No.
So the second point is imagine. Sorry, let me just imagine you're looking at this, and imagine you're looking at something that's 50 miles flat, right? You're not going to see anything past this point. Whatever the scale, yeah, there's going to be some scale variance, but the scale past this point, you would never see any of that. It would be totally compressed. So if you're looking at flat horizon or flat water, it would be compressed. You wouldn't see any more of it.
You're looking at something that's parallel to your line of sight. Of course, it's going to be, almost invisible. But we're not looking at things that are parallel to our line of sight. We're looking at things like mountains and boats and buildings, which are perpendicular to your line of sight. Their change in angular size is pretty much zero with a change in elevation.
Incorrect, because there's foreshortening on mountains. No, there's foreshortening on mountains.
Foreshortening? What is this foreshortening? What's that mean?
You've just seen it on your screen. When something, if you tilt something, a better explanation I can say, if I get a 1 meter ruler.
So sorry, what we've just seen is foreshortening. Yeah, because it's parallel to your line of sight.
Yeah, that's exactly
things that are perpendicular to your line of sight. A change in elevation, like a tiny change in elevation relative to the distance you're looking at, is not going to change its angular size.
But a perpendicular thing is like a 1 meter ruler standing directly out of the ground. Yeah, mountains are not like that. They're at a tilt.
What do you mean, a tilt due to curvature?
No, at a tilt because they're mountains. When you walk up the side. Okay,
they're sloped.
No, well, listen to what I'm saying. So I've got a 1 meter ruler, a couple of meters in front of me. Okay, it looks, whatever the angular size is, it looks like a 1 meter ruler. I now tilt that backwards 45 degrees. If you take the tip of it to the bottom of it, it is now foreshortened and therefore smaller.
Yes.
It's still a 1 meter object, but it is foreshortened and does no longer match the angular size of a 1 meter object.
But something that is 60 miles away, right, tilts away 1 degree, right?
Mm-hmm. 69.
That's a very, very small amount of this foreshortening. Do you agree?
That's not foreshortening. That's degree dropping, isn't it?
Are we talking about tilting away?
No, foreshortening, how I see it, is if you're a 6 foot person and it's based off of your acuity of your eyes. If you're a 6 foot person, you can see 3.9 miles with a perfect eyes into the distance.
You can see. Are you saying your vision is limited to 4 miles?
No, listen to the floor.
I am.
So if you were to have a train track in front of you, you will be able to see rung separation up until around about the 3.9 miles where everything converges into 1 point. If
so
that
you're
makes
talking about
any
diffraction
sense.
limit?
Well, that is what is included within it, but it's the diffraction limit of the floor. Obviously, if you have something double your height, then it will appear, because
you guys know there is a formula to describe the diffraction limit, right?
Of course there is. Yeah.
Okay. Have you ever applied it to a long distance observation?
Yes.
Have you? Let's apply it to one now. Let's apply it to Canigou.
Hang on, before hang on, wait a minute.
Misdirecting.
Before we get too far.
Because I wanted to either way add on to this actual platform one, and I would like to back up Travis on this one, and I think Chris backs
Travis
him up
admits
as well.
that it's admits that it's not a factor in these observations.
Right, hang on, guys. We've got I've had a couple of super chats from somebody who wishes to comment on these particular images that we have on screen right now. This is what if you asked me to put these images up. So Elijah Freeman says, I've been saying that the second video, the image is taken from slightly lower than that, our habitat 1 foot is potentially 2 or 3 feet. I would have to disagree with that, because I think
this is a different video.
Yeah, this is a different video. This is a different image. This is a different image. They're two completely different images to this particular image, the Black Swan image that we've been talking about. But essentially, hang on, I forgot what I was going to say now. Yeah, you wanted to talk about these images, and also he's done another super chat, and he says distance to the bottom of a building is less than the top if you're on the ground level. Looking at the top of building versus the bottom literally changes the angle. You would have to agree with that.
Hang on, let me read the super chat. Distance to the bottom of a building is less than the top of your ground level. Yes. Looking at the top of the building versus bottom, yeah, it does, only if you're very close. But when you're talking about long-distance photography at like a field of view of 1 degree, then that really doesn't change.
Oh, well, hang on, wait a minute. You asked us flat earthers before, if the platform was 20 foot high and it was 10 miles away, would you be looking up to it?
Yeah.
And then, so how can you quantify that with what you've just said, which is that basically if it's just 1 degree, there's basically no difference?
No, we're talking about two different things.
No.
This guy's talking.
No. Yeah, I know, but I know what you're saying. Yeah. But essentially, you've just caught yourself in a trap there.
No, I don't think so, Randy.
Yeah.
He says distance to the top of a building is less than the top if you're on ground level. Correct. But when you are a long distance away with a very small field of view, like if you use this Habitat Grace as an example, right? If you are on the ground versus 75 feet up and you take the distance to the top of the oil rig and the distance to the bottom of the oil rig, it'll be negligible, be close to zero.
Can you guys hear me?
Yes, we can, yeah.
Yes.
I don't see anything. I'm sorry. I'm in the Skype chat, but I don't see anything.
I'm on the watch page looking at the...
It's on the live chat.
Okay.
Right, okay, so you can't see this image on the watch page then?
Yeah, can I just add
I'll copy it and
I'm not on the watch
it.
page just yet. I got to open it up. I'm going to open it up right now.
Can I just add some clarity? What I think that Ruhif's coming across as is if you were to take 1 foot of the legs above sea level of the first platform on both of them, that will be a straight perpendicular line running alongside with the flat earth. 1 foot, 1 straight line. If it was a string from your center of your lens to 1 foot above sea level there, that's a straight line. But then if you go over to the second platform on the right and do the same thing and put it 1 foot on the legs, then you should have a straight line with the string. And what he's saying is obviously the one on the left you cannot do that with because that will hit the water, this solid lump of water.
Correct.
Yeah.
Well done.
Now, what I agreed with on Travis-wise is that the back image does move. And I know that sounds as if it's ghostly, but that backs up exactly what Ruhif says and exactly what Travis has shown. And I would have thought that Randy's shown this as well, where a sea line can rise, especially at high tide.
Can it rise to above eye level? Can the horizon...
It can rise up enough at a certain point. All it takes is one wave above 1 foot in the distance in order to block something even further in the distance.
Ruhif, what is the actual with this photograph? Would you mind stating?
On the screen now, on the watch page, it's a looming. Randy's asked for proof of looming. This is it.
Which you're saying that the one on the right is looming?
Well, technically they're both looming, but we'll ignore that for now. One on the right, the back oil platform, is clearly higher relative to the one on the left.
And is this taken by the same person with the same camera lens?
Yes. Same. Yep. He actually says in the video.
Same observer height.
Yep. He says different day, same exact location,
same observer height.
Same observer. You're gonna, Ruhif, you're really gonna go down this line, and you're gonna look at this image, and you're gonna
really gonna call your favorite blogger.
Wait a minute. You're gonna tell me that you were gonna look at these images, and you can't see, for just even being honest right now, that even if he's claimed it in his video, that you know by looking at these images that they are not taken from the same height. Be honest here. Don't be a typical globe head, right? Look at these two images and say that they were taken from the same height.
I believe the guy. I believe the guy.
No,
What the
Ranty.
original photograph to show without the annotations.
Yeah, I believe you're right though, Ranty. That is your original initial thoughts. That exactly that,
and that was with this guy. You're either calling him a liar or admitting to looming. You can take your pick.
There's a difference.
It's not liar. There could be something else involved.
Oh, come on! If he says this is the exact location and the exact elevation, you know.
No. I mean, from Ranty's point of view, Ranty, there could be refraction involved, moving the scene.
Yes, there is. Yes. Well done.
Opposing types of refraction.
Are you
one
aware
it's towering, the other it's actually
how is the one in the front? How come we're seeing the bottom of that?
sinking?
Because the horizon is supposed to be 1 point. If this is the same place, how far out is Grace?
I don't know. 20 miles, something like that.
Can I ask
that's the 9-mile one out. Is it the one at the back?
I've got like 1 minute. 1 minute, people.
Yeah, can I ask a dead serious question? A dead serious question.
I'm going to share. Can I share my screen a second, Randy?
While you're doing that I just want to ask one question. Ruhif, are you aware of what relativity is?
As in Einstein's theories?
Yeah, well, just the whole concept of what is wrong with me saying, on one hand, the left image is showing Earth curve in its natural state. The right image is showing refraction. Or
they're
on
both
the
showing
other,
refraction, by the way.
No, I know, I understand. I'm just saying the reason why the scenery is like it is. And then what is different to then saying, oh, it's a flat Earth, and the left one is actually showing a sinking effect due to refraction, and the right one is showing the true image. What is the difference in saying that?
Difference is, he actually says in the video, I went to film these platforms every day for 3 months, and they were always like the image on the left, and one day, conditions were different, whatever, and they came up on the right. I got to go. Thank you for having me, Ranty. I enjoyed it. See you later.
See you in a bit.
What?
Yeah.
So the one to the
off too easy there with this nonsense. He didn't provide enough evidence for what he was claiming. He just has this photograph. He doesn't provide more than that. He doesn't know the distances to Grace, stuff like that. All these kind of things. He's not providing enough evidence. And he disappeared because that's all he wanted to do. He wanted to come in and argue the minutiae. Where's the 1.22 hard horizon that should be here? It's not there. If it's from the same 1 foot observer height, is it? I don't know because he's not giving me any details on it. There was no details given there. He just came in, presented that, and went to run off. That's basically all he did.
Okay, so listen, guys. This is monumental. Okay, I am absolutely convinced. I think I said this earlier on Chris Berry's stream. I've never said this before. This is the globe killer. This is monumental because what we observed with Jose's show on Friday when he read through the HTML from the EDU site on refraction and the vanishing line, what you're seeing when right here is the vanishing line. And what the vanishing line implies is that there is a mirage. Everything below the vanishing line is obscured. Everything behind it is obscured. Even though you don't have an inferior mirage, we have to have a new classification for this because this is a mirage. There's just no inferior mirage. There's no superior mirage. Okay? So I've shown this on my stream. I was going to do it again tonight. Ranty, you've got your live stream right now. I'm simulcasting right now, so you're on my channel. But whenever we wrap this up, I'm going to jump over and just start going through my footage and demonstrating over and over again this stuff. Like I said, and nobody seemed to want to touch it. I've got my oil rigs that you can only see the top rigging. The whole body is gone. The elevation of the water is up to and goes over the top of the oil rig. I mean, it's that insane. There's no way to get around that. That is as far as I know, that is an unclassified mirage because no one thinks of it that way. It's like, dude, it's like the murderer that's out and about when the prosecutor and the defender are focusing on the wrong suspect. They're looking at the clues incorrectly. and they don't see what's in front of them. They just don't see it.
Can I share my screen briefly, Randy?
Yeah, of course you can. Yeah.
1 sec. Just this. Remember this photograph I shared at the start of Mount San Jacinto, taken from the same location by the same person, same camera. Just
I think I'm going to jump out, guys. I'll catch you later.
Okay. Yep.
Yeah. So I'm gonna start my stream. I'm not trying to compete with you, Ranty, but I just want to get my stuff out there. So appreciate it, mate. Talk to you later.
Yep. See you in a bit. Bye bye.
There's 2 photographs taken by the same person from the same location, and in one the mountain seems higher than the other. Just different lenses, different days. So, is the one on the left loomed up? Is the one on the right sinking? It seems to me like
magnification. Could be.
Do you want to reshare your screen again there, Brian?
Okay.
So I'm trying to find the mind of God's the mind of God on my Skype, and I can't find him for the life of me.
There you are. See, what Ruhif did is he came in, he argued the minutiae of the platform photograph, and he tried to argue about every bit of nonsense except for explaining the Howard horizon. Right? He wasn't touching that, right? And then he threw out this other photograph that he didn't even have details for. I said, "How far away is Grace?" I don't know. Do you know what I mean? Like that was he didn't even have details, and then he just like a drive-by nonsense, like someone put in the chat. It's like just the woman and run off. It's pathetic. Like if that's what he's going to, that's the best he's got. Like.
Yeah, the core I got from the whole argument is when you come in there and said basically, so all you're saying is that the majority of the time it looks like a flat Earth, but it really looks like a flat Earth once or twice. Because it defeats that. That's what I don't get. At 1 foot, the horizon line should be at 1.22. And even at 6 foot, 3 miles away. And they're sort of like 6 and 9 or something, aren't they?
Yeah, and we don't know how far away Grace was, because Grace is a different one. There's Hilltop and Habitat, and Grace is a different one. So we don't know how far away Grace is. And he said for 3 months that the guy supposedly took the same observation. It looked exactly the same as the one on the left, and then one day it looked like the one on the right. Now, something tells me that that's not possible at all, because every day it's going to look different. Because you won't have two exact. The only person I know that got the exact same observations, is Tim Osman, and he had to wait the best part of 3 years to get it. His recent observation is nearly an exact copy of his original observation for 2017, right? But he had to wait for the exact same conditions. He was out there getting observations that he wanted shown to people, and then he gets the same, nearly exact same replica, carbon copy of the original observation, and he come back, see, proof. It's like looking for the same exact observation. You won't get it. You won't get the same observation like every day for 5 days even in a row. It'll never happen. It'll always be different, because weather will always be different.
Yeah, straight.
So Ruhuf saying he got the exact same observation for 3 months and then one day he got that. That's a total lie. It's a load of lies. No, he didn't.
Yeah, on those observations, though, he's using it exactly for that, though, to say we shouldn't be seeing this at all. That's the whole thing. By the geometric, even including refraction, you shouldn't even be seeing that. It should be hidden behind curve.
Yeah, I mean, there's no hard horizon in photographs. That's the problem. If it's from a 1 foot observation height, there's no 1.22 horizon. There should be a hard horizon.
What's his argument for that? Like, what was his statement of the infinity? Did anyone understand that?
Kind of.
Infinite 7/6 refraction.
Is the old, if a beam of light gets trapped in a duct, it's got the ability to, if it doesn't fall victim to the inverse square law, it's got the ability to go right the way around Earth and come back on itself.
Okay, so he's leaving the 7/6 alone. He's making R infinity to make it essentially a flat Earth, right? Like
exactly.
from the...
Exactly.
Okay.
Exactly.
Well, that's insane. I mean, you can't just make up a shape that's convenient for what we're seeing.
Yeah.
What I would say about it is that it's either all this crazy minutia of stuff that turns it from a globe into a flat Earth, and that's only individual. That's not even taking all the other parts of the globe into account, like, you know, gas pressure, whatever the container, and rotation and everything else, gravity, name it. We're just talking about just visual. So it's either all this crazy minutia stuff that's making it look flat all the time everywhere, right? And airplanes don't have to account for drop, or it's flat.
No, it's flat for sure. Randy, can I walk through Chris's thing really quick, if you don't mind, just for like 30 seconds, and then
I'll share my screen here. Sorry.
Sure. Yeah. Fire away.
And I just want to explain the significance of what Chris showed, and I think it's important because it's very simple and elegant. So, what he's showing across a flat surface, if you put that piece of paper with that red line on it, or any line on it, if a person is going to model that mathematically, and let's think of this just as binary, like visible or not visible, we're not going to actually just reproduce the red strip. Let's just say we wanted to come up with a mathematical representation of when we could see that red strip or not. And so he showed high angle, you can, you know, not a surprise. Then he drops it down to close to zero, and then you can't see it. And then so in that transition point, you go from red being visible to not. And then he pulls the piece of paper close to the camera, and then it becomes visible again. And so across a flat surface, and he demonstrated that it's flat and straight, angle matters and distance matters. And so that's really the fundamental argument, that we understand that the paper's thin, we get it, it's not really supposed to be visible, but the fact that it can't be seen when the camera's against the table is the point. That's the whole point of it, that something very thin will not be visible relative to the table in a short distance, but the mathematics that would be used to decide whether we can see that red strip or not would still hold if we explode that out. Ballers, I guess, would have to say that it wouldn't. They wouldn't even go to an attempt to model that mathematically, but that math would hold. You know, if we were to stretch it out to a mile, replace that red strip with the first floor of a building, you know, then a second floor and a third floor and all that kind of stuff. So I just want people to know that something like that, tests like that, across a flat surface really challenged what ballers know about optics, which is clear that it's very little from what Ruhiv said. That's all I got to say.
Yeah, excellent. Yeah, let's not gloss over that. That was an excellent presentation, an excellent test that showed that example that Nathan was trying to do with his book over the floor. But I think this was a better way, because there's no divots or anything on that particular surface, and it's, you know, it was such a thin piece that was, you know, it was just really good.
I think they missed the point of Nathan's too, because it was kind of a while back. I think it just went over a lot of people's heads, including our own. But Chris proved that it's straight. There's line of sight. No one can argue that. Yeah, the paper's thin, but that's the whole point. It's not that far away. It's a pretty small table. You should still kind of be able to see that there's a paper at the end of the table, but you can't. And that's the whole issue with the angle. It's very sensitive. Our optics, whatever it is, puts a premium on height. That should be common sense. But I mean, a lot of these people are just actors and shills, but they should know this. You know, you stack 50 pieces of paper, of course it's going to be easier to see than one or two. Like, it should be obvious, but I think it's a good demonstration. And yeah, Ruhiv has no idea what he's talking about, dude. That's insane. Whatever he said to defend that is just ridiculous.
What Ruhiv was doing is he was trying to point towards the white swans. And this is what the game is. Keep pointing towards the white swans and forget about trying to avoid that there's a black swan. And that's Quantum Eraser's argument on this, is that there is a black swan. The photograph of the platforms with the horizon at 10 miles out is the black swan. But the other observations can be explained on the flat Earth. We can explain that, no bothers. But that observation cannot be explained on the globe, and that's the problem. So the whole thing is now to keep on pointing towards the white swans and ignore the black swan. That's the direction, you know. That's why it's been called black swan photograph. And that's the thing. I mean, someone like Ruhiv, from my experience with him, he's willing to say anything it takes, regardless of if it's an absolute lie. He's willing to say it just to try and win a point in a debate. He doesn't care. He'll say it. He doesn't matter
he
whether
was
it's true or not.
uncomfortable, man. He didn't want to talk about it. You could tell he wanted to switch the topic. He wanted to fix his air conditioning. He wanted to do something else.
Yeah, exactly. As soon as any questions start coming about the thing, I asked him to share the photograph without the annotations and stuff like that. You know, how come his black lines are so big in these annotations? They don't need to be that big. They can be coloured and thin. They don't need to be that big. But, you know, just share it without the annotations. You know, give us more details on this. And he's gone. You know, or, you know, air conditioning. Sorry.
The vibe is kind of funny because every time you guys produce something that is not visible on a ball earth, Rumpus and Philip have to go fire up the super loomer, heat that thing up to get it to work. And then now this guy had to heat up his 7/6R to infinity to make it flat. So, you know, technology's catching up to these people, man. Optical limitations was what caused the ball earth to exist. And it looks like it's, you know, it's disappearing, literally, like it's evaporating the evidence of a ball earth. So, yeah.
Did we call it infinite over 6R?
But it's really the R that's infinite. It's not the 7 that he's changing. He's just doing that to sound smart. It's 7/6 is a constant. That's what they claim is a standard average refraction. It's really the R. It has to be an infinite loom, I guess.
But see, that's another thing. I asked him earlier on. He was talking about the refraction. He was talking about the atmospheric effects on the habitat platform in the platform photographs. And I said to him, I said, how come if it's all being loomed up, which is basically what he was trying to say, for a start, it has to be loomed up either above or behind an horizon. That's number one. And number two is that you have to have uniform effects across the whole observation, which he doesn't have. There's no uniform effects. The effects are different from part to part in the observation.
Yeah, agreed. So he's saying the horizon looms up, and then he's saying some of those objects are looming up over a local horizon. So there's like double looming for him.
Yeah, he doesn't. Yeah, like the looming is only happens. Looming is based on a radius, and the looming they're speaking about, that's based on a radius, and that only happens supposedly over and behind an horizon. But the horizon, all this stuff is in front of the horizon, and it's a completely different across the observation. There's all different effects happening. There's not uniform. For that whole thing to be, if you see a mirage of any kind, do you see a different one part of the mirage to be look different than the other part, or is it all the same effect happening? You know, that's the whole idea of it. You can't have different effects across the same observation and still say it's all the one thing, if you understand what I mean.
I just found it funny that he started nitpicking on like the arm of the rig, as if that little discontinuity, those jagged things, are like what would motivate a horizon being loomed up. Like, that's insane. Like, I don't even know what to say. Like, I think he's joking when he's kind of saying it, but pointing at that as evidence of an unclean image, to me, I don't even know if we can take him seriously. Like, if he's joking or if he's...
He can't be taken serious. What he actually said was that you wouldn't see it bend if you were close to it. But of course you wouldn't. You only see these things at a distance. You don't see, like, I mean, a mirage doesn't happen right in front of you, but it will happen at a distance. You know, if you see the roads shimmering on a warm day, you won't see it happening underneath your feet, but you'll see it at a distance from you, you'll see it. You know, he's saying, how come it won't be bent? So he's saying, well, he was saying, but if you're up close to it, you won't see it bent. You know, or wavy and bent. It's like, of course you won't. You only see these things at a distance.
Yeah, that's obvious. Yeah, he's answering the whole question. He's saying the more distance you add, the more ambiguity, the more choppy an image will be. That's just obvious. So I don't know if he knew that he was hurting his point saying that, but it doesn't make sense. Yeah, if we were really, really close and there was that kind of distortion, yeah, then he'd be like, dude, there's something really weird going on in the atmosphere, for sure. But you're pretty far away. And like Ranty was saying, maybe it's a different temperature than the rest of the structure.
Yeah, it's a funnel, isn't it, to get rid of the fumes, and sometimes it's on. You know, it has a flame at the top of it, so it's going to be substantially hotter than the rest. So, what can you say?
And Ranty, you know what's cool? If somebody did do a time lapse of that, you know, I know it's a static image, but if you time lapse it and average it out, that would show as well that it would probably average out to the actual structure, but the horizon wouldn't average out to something different. It would stay there, you know, in the far distance, assuming again that we're on a flat Earth because it's physical. that's creating that. And so, I mean, again, it's an image and it's still really good, but if those things average out, then we have a sense that it's something local that's distorting that.
Shout out to Elijah Freeman for another super chat who says, yeah, the difference in those two vids is maybe 1 foot. Yeah, I'll agree with that one. And lastly, the Mind of God. Great hangout, very edifying. Thank you very much. Were you there anyway? You're there, Shirag.
Yeah, I'm just going to drop, but I just wanted to go through Chris's thing because I just think it's very important because it looks like all these ballers, there's very root level differences that we have technically. I don't think it's wrong for us to highlight them. It just looks like that's the case. They can keep saying, you know, my hallway's curved. They can say that other gentleman's hallway's curved. They can keep saying that because that's really all they have left. But I mean, now their back is against the wall. I mean, that's a horrible position to be in. You know, I think we've shown bottom up obstruction. I've seen at least 5 or 10 good videos on YouTube. So,
we've got Dean. I don't know if you know who Dean is.
Yeah.
Yeah, Stingray.
Yeah, so would you mind if we brought Dean in? Apparently he's got a little demo on Refraction. I'll see if he's available.
Stingray!
I think I'm going to leave again.
Stingray.
This is getting too baller for me.
It's getting This is getting too baller for you. Don't you like talking to ballers, Arwin?
Not this late, no.
Well, plug your show for tomorrow.
All right, yeah. Flat Earth Early Bird Show, 2 p.m. Amsterdam time, 1 p.m. London time, over at my channel, Arwin, ARWIJN. Yeah, come and visit sometime. Ranty pops by every now and then. So.
No worries. Catch you later,
I'll see you in the morning. All right. See you later.
See you, Arwin.
Take care, Arwin.
So
Thank you.
Dean, Stingray, you've got something for us, you say? Yeah, we can't hear you.
The ballers wake up from their bed when they're getting clobbered. So Rumpus is probably getting his coffee right now. Dean's waking up. They can't just accept that it's flat.
Oh, he's
10 to 2. 10 to
2. Dean's left now.
Joined on the wrong account.
Did he?
He's just going to pull up his flat Earth model with the sun and just laugh and say, oh, how can this be? I guarantee that's what he's going to do.
We'll see that.
It's gone then, Chirag. What do you guarantee that I'm going to do?
Okay. Prove me wrong, dude.
I don't know what you said, so...
Going to pull up his model.
You're going to pull up your model with a local sun over a flat Earth and just say, this can't work because look, Australia is not getting any sunlight or something.
I'll have you know, and Gleam will attest to this, that I found a way to do sunsets and sunrises on a flat Earth. So
he's pretty good. He is actually doing something positive, and I will back him up on that 100%.
Dean, does that involve the sun being high and a big object moving away from you faster than your optics can follow it? So its bottom of it is reaching your diffraction limit, even though, and that's what happens, the bottom of it reaches your horizon, your diffraction limit. But it's actually gone further than your horizon would be.
No, because the issue with that is, let's say the sun is 3,000 miles up. I'm going to do some stupid math here because I hate math. But let's say the sun is 3,000 miles up, or 10,000, doesn't matter. For it to go to 70, for it to move 70 degrees, so let's say straight up is 0, for it to move 70 degrees over, not 90 to the horizon, but 70 degrees over, it would have to equal the distance of its height. A little bit more, in fact. And with that, it will double its distance from you. Now, any object that doubles its distance from you will reduce in angular size by half. So you've got to think more creatively than that. And I did. And I came up with it.
But, Dean, why is it? I have to ask a question. On your side of the argument, people are always asking about how come the sun only barely changes angular size throughout the day. But yet, when it comes to the angular size in observations, these things are ignored. Now, I'm not pointing the finger directly at you, right? I'm pointing the finger at people who ignore angular size at all other times until it comes to the sun, something we don't really know much about.
I can't speak for other people, to be honest.
And I don't know. I don't know those
to model,
observations either. I can't see.
It's impossible to model, dude. We don't know the position of it. We don't even necessarily know what it's physically made out of. We don't know the channel that you're trying to model it moving through is incredibly complex. I mean, I don't understand what kind of fruit are you trying to get from doing this aside from maybe laughing at us.
I gave it I worked, there's only pseudoscience now, this is pseudoscience. I worked out that it was about just over 300 miles up, and it was about, I think it was 36 miles wide or something like that. Possibly, or was it 54? I can't remember now what it was, but I worked it out something like that. That the sun was possibly that, but I can't prove any of that. I can't. How am I supposed to prove any of that? I have no idea.
Exactly. We would have tried already if we could.
Yeah, I mean the issue with thinking of those it's Brian, yeah. The issues with thinking the issue with thinking of those actual physical dimensions. If it's 30 miles up, for it to get 60 degrees away from straight up from you, it only has to travel 65 miles. 50 odd miles. So because it and at that stage, no matter how big it was, due to the laws of perspective and angular size reduction, it will reduce by half.
Yeah, but what is your visual limit as a normal person? What's a normal person's visual limit? A few miles.
No.
3 miles is kind of the limit, isn't it, from most people's eyes?
No.
Well, the horizon, they say, is about 3 miles away normally.
Yeah, but the horizon is not a visual image limit of your eyes. You can see beyond what you would call the optical horizon.
Well, how come you can't see out to sea further than what the horizon shows? I mean, I've never been able to see past the horizon.
Well, as a flat Earth proponent, I would say it's the diffraction, optics, something, blah, blah, blah. But as a glober, I would say that's the curve of the Earth.
No, that's not making sense.
Yeah, it's time varying. It's time varying and statistical. That's why.
I've never even met someone that could see further than the horizon. Because the curve of the Earth, if you're claiming the horizon is the curve of the Earth, then how come the horizon moves and gets closer and further and up?
So there are two. Yeah, no, so I can answer that.
Yeah, that's what he said.
So there are two aspects to the horizon. One is the physical geometry of the situation. We'll call that the absolute truth. And then the second is the optical observation. Now, can the two match? Well, if you're asking me, can they match? I would say, in most cases, no, they won't. But they can be close. Now, can they diverge? Absolutely, and we can see that, and we can demonstrate it.
I don't see any evidence in 5 years to support that. I
can answer it with a question then.
Okay.
If you go to the same, so Travis is best to answer this. If I ask Travis this, I'm going to guess the answer.
He's not here now. He's gone off.
I know. I was going to pop to his channel, but he's just watching yours, I think. So if I have asked Travis this on Jose's channel, I've said, if you go to the same spot, take multiple observations on different days, are all the observations the same? And the answer is no.
No.
Great.
Agree with that, yeah.
Right. Okay. So does that mean the physical reality of the situation, as in the geometry of it, is constantly in motion and changing? Is the Earth, or what we call the Earth, or the land masses, are they moving up and down? And the answer is, to me, no, because we don't see that, and there'd be terrible earthquakes if it were. So that means something optically made that move, and we call that refraction. Yeah.
No,
because it's. Listen, let me just finish first.
Okay.
Wait, let him finish.
I'm literally a sentence away from finishing. So we call that refraction, and it's the bending of light, and the variance is because there are different atmospheric variances on each of those days, and that's it.
Yeah, but the problem is that we see further, right, and with a higher horizon, we'll have a higher horizon, right, in observations on a clear day. On a bad day, the horizon will be closer and lower in the same observation. Now, that's because the horizon is not a physical location. But on the globe model, the horizon is a physical location. And this is where the problem is.
Okay, so I mentioned two things to me. So you're addressing me. So there is a geometric reality and there is an optical reality. And I just mentioned the two can get close. I don't believe they will ever sit on top.
Shout out to Elijah Freeman again for Globe Earth Super Mario Looming Infinite Refraction. What a super chat. Awesome, thank you.
1 second. Let me just respond to that. So it's either a whole minutiae of refractive craziness that's a globe always looking flat, or it's just flat.
Wait, I just want to address that point, Dean. So kind of in line with this. So do you?
I haven't spoken to you in ages, actually, Chirac. Hello.
Yeah.
How are you? Happy New Year.
Yeah, you too, man. Happy 2020. So just to clarify, would you agree from like a statistical perspective? Let's say that we were to take observations in a fixed place across, water or something. If the Earth was curved, we would see less variability in the horizon, right? Because you're talking about a fixed curve creating a limitation in viewing versus a flat Earth, we would potentially see more variability. Do you agree with that statement?
Wait a minute.
Because it's anchored by the curve. The horizon, you believe, is anchored by a curve, though it can change optically, right? Like
so
to some degree.
Right. So the important thing is when we observe it, we are observing it optically. We are not observing the geometry. And I've just said the optics of the situation can change a small amount to a dramatic amount.
Okay, so you think even on a ball that it can change dramatically, even though the horizon anchored by the physical curve?
So the interesting thing here is the horizon is an optical observation. Based on that, you cannot tell where the geometric horizon is. So there is no anchoring there.
No, but you believe that, let's say again, this is statistical because we're looking across a time-varying statistical channel, right? The atmosphere. You would agree, though, again, I don't even know if we could even do a test like this, but it would be less variability in the Earth curve in the ball model because the horizon is at least governed, limited by the curve of the Earth, right? In the flat Earth, it's a long flat plane. It'll take on whatever we can see based on the atmosphere.
Well, yeah,
so the horizon can change.
Yeah. So the issue with the flat Earth, and this is an issue that I haven't solved yet in any singular way, is on a flat Earth there is actually no hash horizon. And the reason for that is the horizon is a geometric cutoff point. If you were to say a flat Earth horizon is because of the extents of vision, then we would not see a geometric dead end. We would actually see a gentle fade into nothingness.
Yeah, which is what we see.
We would still see an horizon.
Oh yeah, gentle fade into nothingness, and you would have to ban that gentle fade as the faded horizon.
Well, let me ask you this. You know the way we see the horizon coming closer and further with weather and higher and lower in observations with weather. Mm-hmm. What is more likely? Is it more likely that's happening on a flat Earth, or is it more likely that's happening on a globe?
The geometry of the situation doesn't really matter whether it's flat or globe. The thing that in a flat Earth, then I would expect to see. So, if you take premise number 1, refraction happens and it bends light. If you take premise number 2, the atmosphere is more dense low down and less dense higher up. And if you take premise number 3, Fermat's law holds. Fermat's principle holds, or Snell's law holds in how light works within a change of medium and density. Then you can actually say, you can infer that, well, hang about, if we've got a sphere can present as flat. But on average, you can go from spherical to flat to maybe a little bit, unflat, let's say, a little bit concaved. Yeah. Now let's take the flat Earth and put those same variances back down, and we'll say, right, well, given this, what happens now? Well, it could present in extreme circumstances as a slight little curve down, but it will mostly present in a very harsh arc upwards. So your variance will be between a little bit up to very up. Yeah.
No, that's what we're trying to appeal to you, Dean. Is statistically, the flat Earth makes more sense because it's open to more variability in whatever you call it, the optical horizon or whatever. So again, this is not a proof, but it's more likely that it's flat.
Oh yeah, there's so in this debate thing, I wouldn't ever. People keep saying, "Oh, I've got proof. What you've got is evidence, and then there's a weight to that evidence whereby you can weigh up against your whatever it is you're arguing for. So it's never proof; it's evidence.
So can we say you're statistically a flat earther as of January 19th? Or is that too strong?
No. Yeah. Way too strong, mate.
Can I answer your question, though, Dean?
I don't know what it was now, mate. So if you refresh me on the question.
Definitely. How flat Earth can explain a hard horizon?
Yeah, go for it.
Okay, so I'm going to completely forget about the last 0.02 degrees where you see the critical angle of light, where the reflection is over water. Okay, so if you were to look into the horizon for the limit of your eye, and we won't get into the calculations, although I can give you the calculations if you want, but if you imagine, and it will take a thought experiment, but if you imagine exactly what Ranty said earlier, a train track going off into the distance, but instead of actual rungs of the train track, all it is meter markers being 1 pixel in width. Okay, so they are going to shrink as they get into the distance. However, you know that they'll compress. The lines will actually compress as the further they get to the horizon. Yeah. So when you get to the horizon, which is the limit of your distance of the surface that you can see, you'll have 3 or 4 lines sitting on top of each other. And that is your hard horizon there.
Right, let me ask you a question on that. It's very important, or it's a very pertinent point that you said, let's not add calculations to this.
I can do, though. Yeah.
Okay, so an observer height at 6 foot on an infinite plane or an extended huge plane that's like tens of thousands of miles. That tens of thousands of miles will rise to eye level. Rise to your midpoint. Now, the issue that I've got there is that will not be a geometric occlusion of anything because it is the base of everything. And the only way that will fade out is due to the extents of my vision within the atmosphere, and that is not a cutoff. Now, what you were talking about there in games, that's actually what we call texel ratio. It's the ratio of normal, surface normal based area versus the sensor medium. In a computer game sense, the TV screen. In our eye sense, the rods and cones. In a camera sense, the lens. And yes, there will be diminished capacity to discern detail, and it will actually kind of end on a line. But that line with a 6 foot observer height will be tens of thousands of miles away.
No. I beg to differ, and I will show you the maths if needs be.
It's basic trig, so let me do it right now. Give me a
yeah,
second.
no, it is basic trig. It's tangent. It's the height over the tangent. But let me explain how the maths would work, where you have height, obviously, height off of a surface, and there would be a triangle between your feet and your eyes. And just as you said... I love the way that you said, no, there are 2 separate things going on here. You have a separate optically distorted view, and then you have a geometric reality view, which is exactly what perspective view versus geometric or orthographic or what is it, Muppet vision that they call it is. And so the same thing that you're promoting.
Wait a minute. So orthographic is a form of perspective. Never call it Muppet vision. It's just a way to isolate yourself from the situation and show it in diagrammatical form. A perspective view in 3D represents the geometric reality that we would see if there was no atmosphere there and we were viewing stuff in a vacuum, let's say.
I beg to differ, because orthographic view actually destroys all angular resolution changes.
No. I said, so a perspective calculation can include an orthographic view transformation.
Sure.
But what I'm saying is a perspective view that does have field of view. You do incorporate sensor size, and it does give you a nice perspective view, what you see with your eyes, which would be an equivalent 35 millimeter or whatever.
Yeah.
I'm saying that view, when I use it, and I've got a camera in 3D, that does represent the geometric reality. Now, what I can do in a rasterization engine or a ray tracer is I can put in the atmosphere or what the atmosphere is supposed to be doing to compare that to.
Sure.
So I've got the geometric reality, then I've got the reality with the simulated environment in it, and I can compare them against the actual photos.
Yep, sure. I fully understand that, but
Andy, my screen.
But I really want to add on to that and say there is not just a refraction. If I was to do an analysis and to say, right, I've taken a photograph, what do I need to account for? And I would say there are three main things. There would be one, your device distortion. Whatever equipment that you're using to capture that data will add distortion regardless, and you need to account for that. For example, with a camera, it would be slight lens distortion. You could account for if at long distances little fractional details matter. But then you have your environmental, which can be your actual sky and your other, could be fog, could be anything, whatever your conditions, your temperatures and whatnot.
I'm really sorry to interrupt you, just really quickly, because you will know the answer to this. I am listening. What's the Rayleigh criteria for the human eye?
It's if you were to take the proper volume, it's 1 arc minute, which is 0.01666667.
Okay, cool. Cheers.
Cool. Randy, can I share my screen, please?
Hang on, hold on, guys. We're joined by Carlos. Carlos, can you do a mic check?
My connection's not that well.
Yeah, you're coming through fine. That's good.
You sound cool.
Give us some pills. Get a better connection.
And sorry, just to cut that last bit off. So the three considerations was your equipment that you're capturing, the environment in which you're capturing in, and also your perspective and distance distortions. And there are distance distortions which I believe can be calculated in.
Yeah, no, so the perspective is, believe it or not, I learned about perspective because, I've been a 3D visual effects artist. I know about perspective, but I assumed that the perspective algorithm has been around for thousands of years, and I was surprised to realize that it might have been lost in history. I suspect that at some stage, because the Romans could draw perspective very well. But then in the Renaissance, so 500 years ago, they developed the distance the distance and size reduction equation, which has stood for 500 years and what represents our reality. And it's why the Renaissance created some amazing paintings based off this calculation. So perspective is not something to really you have to consider. It just is. And if someone wants to invalidate that, that's fine. I'll go with you on, yes, the equipment. So the equipment's incredibly important. So the lens and the sensor, incredibly important. Atmospherics, incredibly important. The lens and the sensor, I can account for, and I can explicitly say, haha, these are known quantities and these are the variances. The atmosphere, I can't. So the one thing I hear, that I always see a problem with, it's always, and it doesn't matter which side it is, it's either true or false. It's binary, when actually it isn't. And if you said, and it's always a case of, oh, well, give us some figures then, and if they're slightly off, then your whole argument's shot. We never deal with error tolerances or variances, but the atmosphere presents a huge variance, even just in a couple of 100 meters, let alone the types of, the 3 kilometer, 5 kilometer, 10 kilometer observations. So you always have to account for variance. Now, this is the last thing I'm going to say. I did glance at the pictures of the rigs and stuff. There's a general rule. If you logically say that light is being distorted from here to there, and that's a given. If you don't think that's the case, then that's interesting. You'd probably have to prove it, because we can prove that that's what happens. Now, if the light has been distorted, it becomes, what is the variance that is being that is there, and how much can I trust what I'm seeing? And if you take one premise, light distorts the geometry of the situation to a varying degree based on the magnitude of the effect. So when you look at the oil rig and you see, or a building, and you see straight lines that should be there, the crane, the side of a building, and you see that they're wavy, and you see that they don't match reality, and in some cases in video you see that they're dancing around like jelly, and then you look at that and you say, well, if I go up to that building, is it doing that? The answer is absolutely not. It's built with straight lines. So you can now say, well, the magnitude of that effect is great because it's making the building dense. Now, if you look at an image where there's a lesser effect, and you look at another image that is near perfect, but it's still got a little bit, which one of those three images do you think represents geometric reality? Since you have the ability to walk up to the building or the ship or the rig and say, are these straight lines? And I would always argue the one with the least distortion represents the best reality. Sorry for my monologue.
Yeah, you could say that, definitely. And I could equally say that then why did Soundly settle on his bendy pylons and his actual, I don't know whether you've seen his little 2-minute thing that he done when he done of the bridge, where he's got a water they've got them big white water balloon things, aren't they, out in the States?
I don't know.
It's like a water tanker, but it's a big, like, it looks like an air balloon on a stick, like a lollipop stick, massive ones standing outside of Earth, but it bounces up and down. So you can say the exact same thing about his footage, but all globe Earth.
I really haven't seen. The one thing that you got to know about me is I don't really watch flat Earth videos that much.
His is the most famous.
Can I share my screen, Randy?
Yeah, you can do. But I just want to get a couple of questions out to Stingray just before I forget. But you can carry on, Brian. But I just want to get these questions out whilst they're fresh in my mind. We have a couple of questions from people in chat. First person says, can you explain what you've done to solve the sunsets issue? And secondly, is it possible for you to define what infinite R means?
I don't know what infinite R means. If you I deal with. I think you're relating to the K value matching the radius of the Earth.
Infinite 7/6 R refraction.
It's infinite over 6, not infinite over 7/6.
Oh, infinite over 6.
Yeah, that's it.
I assume, I don't know, but I assume that the variance of the light refraction. So light refraction is based on, if we go with Snell's law, it's the angle of incidence and the density change where you can work, and the normal direction of that boundary where you can work out what the light is going to do. Now, unlike what many people think, and indeed I thought, whether it goes up or down is not whether it's passing from a denser to a less dense or a less dense to a more dense. It is the magnitude. The magnitude is worked out from the angle. The direction is worked out from the angle of incidence, and the magnitude of where it bends to the normal of that surface is dependent on the density. But it's always going to bend on a sphere downwards in that case. And when you say what's an infinite number there, that would be, as someone said, I've just figured it out. They're saying that about the oil towers.
That was Ruhift made that claim earlier.
Yeah. So all that's meaning is the refractive index, or IOR, the units that are in use, or the K value is matching the arc of the Earth perfectly. Therefore, it's presenting as flat and would do so continuously until your vision ran out. If that band of air and the boundaries between it, the K value, was matching the Earth exactly.
But Dean, is that not pre-assuming radius?
Yes, that's a relationship to the radius.
Right.
But just really quickly, I don't deal with that. I deal with an index of refraction, which is the different way to represent that unit.
Yeah, but the problem with that is that's like a begging the question type of a situation, because the radius hasn't been proven. So to add the radius in and into a calculation is
So Brian, I haven't proven the radius, but I know a lot of people have with measuring equipment. So it might be up for debate in your mind. And I'm fine with that. But the unit that I use, like Rumpus will use a K value, which is which you can relate, which is a direct relationship to the arc of the Earth and the 7/6 hour. But I don't. I use distance and index of refraction of a medium. So if you were to say to me, how would you do refraction in water? I would say, haha, that's easy, because water generally has a refractive index of 1.333. Give it the dimensions and I can calculate it. But that's nothing to do with any radius of the Earth.
There should be a hard horizon in that photograph at 1.22 miles, right? And anything that is said to be looming in any way, shape or form, or refracted in any way, shape or form, should be coming up over the top or just behind that horizon. But that's not what we see in that photograph. That's why that photograph is called the Black Swan, because the horizon is 10 miles out at a 1 foot observation height. It should be 1.22 miles.
Right.
Now,
so in
the
that
whole idea of looming is 1 second now. The whole idea of looming is based on, right? It's based on a radius. So the problem with that is that means that all looming has to happen either above or behind the horizon. But that's not what we see. What we see is an horizon and everything before it. And what we also see in that photograph is what we don't see, I should say, is we don't see uniform atmospheric effects across the observation. We see some effects on the left-hand side, which is further away, and we don't see those same effects to any kind of, or if we don't see them, or we don't see them to the same degree at all, on the right-hand side. So to have what you're speaking about would need uniform effects across the whole observation, and it would need to have a horizon underneath it or in front of it. Do you understand what I mean? Anything else is not possible.
I do. However, uniform doesn't come into it. There is no requirement. So first of all,
well, it is.
So wait a minute. Just really quickly. First of all, terms are very important. Looming, stooping, bloody sinking, whatever. I got asked this someone, and I had a really long conversation with him, a flat earther, about an hour ago. LBB something. On Jose's show, and he came on to challenge me. He says, Dean, you don't even know what the 5 types of refraction are. And the problem with that is when you say looming, he classes that, and others have, as a type of refraction. That's not a type of refraction. That's a description of the effect of a magnitude of refraction. So the stooping, sinking, all of that, that's just refraction. So when I say just refraction, and there is no requirement for refraction to be uniform at all. In fact, in those oil platforms, there is very little uniform refraction there, except on the one that is a little bit clear. We can see that the refraction is more uniform, but on the one where it presents with a 9 kilometer or 9 mile, whichever it is, horizon, we can see that refraction is incredibly non-uniform because the light is bending all over the place.
The point I'm making, though, from our side's argument is that for any of that to be seen past 1.22 miles on a globe, what you would need is an horizon that's 1.22 miles away, and those other things being uniformly loomed up over and behind it. Now, the problem is, for that to happen, you need to have uniform atmospheric effects across the whole observation, because you won't have it looking like it is unless it's absolutely uniform. You cannot have.
Right. I think
uniform effects.
No, I think I get what you're saying. I think I get what you're saying now. Kind of. I think I get what you're saying now. So can I share my screen? I'll show you something.
I just want to share my screen for a second. Something I heard you say on Jose's earlier, and I just want to correct you on it. Okay? Oh, cool. You were showing a 3D model, and you were saying that when the camera height is below the foreground piece, then the background pieces will appear to drop down in height in a situation where there's angular size change.
Sorry, say that again. I didn't quite get it.
I'll show you the photograph. The easiest thing, I'll just show you it, right? Wait till it shows up on the screen. I don't know if you can see it, Jet.
No, I can see it. Oh, you're a Mac user. Well done.
Yeah, I'm definitely Mac. Yeah, I walked away from PC a long time ago.
Cool.
These blocks are the same size. There's 1, 2, 3, 5 or 6 of them at the back. There's one here in the middle and one in the foreground. Now I'm zoomed to the one in the foreground. I have my phone, which is an iPhone 5, turned upside down, and I have the case on it, which puts it to just it's the center of the lens, just over half an inch. Okay, these are half an inch high. These are. So I'm actually looking over the top of this foreground block. Now, if I make a straight line from the top of that to the ones at the back, it doesn't meet the one in the middle. It goes over the top of it. Now, my lens is also over the top of, like my viewing height, my viewing position is over the top of this foreground block. Okay, so in a straight line, right, it looks like basically that it's higher than the middle block.
Do you want to? Can I make an observation on this? Because this is a set. There's another guy that did that tried working out the maths of it in a corridor, and he had a DSLR camera and he had an iPhone. I forget his name. But he did something similar to this, but just down a corridor. Now the issue with this is you said it's all lined up, but lining up a lens is not done the way that you've done it. Now, if I could ask you to put a center line lens in the center line in the middle of the image, could you do that for me?
Find the exact middle.
Yeah, of the image. If you know it's like 600 pixels high, put one at 300.
Yeah, I have a way of doing that. I'll try and do that, yeah. 1 second now. I'd have to do line.
But not where you think it is, where it actually is.
I'll have to go from corner to corner.
Yeah, cool. Oh, make a cross. Yeah, I like that.
But I actually know, I can prove it to you that my lens is higher. I can show you the exact thing. I can do a video and show it to you. No, I'm not going to do it right now, but I can do that. No bother.
Yeah, no, a video.
Because I can prove that. Now, I have another image of the same image, just something slightly different. I think that's about right. Now, there's the center of my lens.
Okay, cool. So that center of the lens, does that line up to your 6-inch block? Sorry, your 1 inch, but whatever the height, the one on the right hand side.
Yeah, a line there. I don't know how straight I can make it, but
fairly does, doesn't it?
Yeah.
So now we can assert that your lens is in fact looking straight down, and it is in alignment with that top. If anybody ever asks you that, this is how you prove it.
Yeah, but you know you're missing something here. You're missing something.
The block in the background.
1 second, let me speak. Okay. You're missing something. I told you something that you didn't think about it. I've zoomed to that. So if I was to bring my camera to that block, I would see over the top of that block.
Wait a minute, sorry, you've zoomed to what? You mean you've cropped to this image? You can't zoom in an iPhone.
Yeah, I have to take this photograph. I was actually I zoomed the camera towards it. I zoomed the camera on the iPhone towards it and then took the photograph, if you understand what I mean.
Oh, right, yeah, I can do.
So that's what I did. So if I was to bring my camera lens to that block, you would see over the top of that block.
Yeah, that's cool.
I'm just going to show you a second image here. For that to be like this line here is mostly the line that's taken when people are taking observations. And they see something in the background, and it appears to have dropped below what seems to be the basically straight line. But it's only angular size change. It hasn't dropped. It's not gone over the curve. It's just gotten smaller. And this here proves that. Because this is just on a countertop. It doesn't have any curvature to it.
Right. So what I would say here, Brian, is what are those objects in front of those blocks?
In front of?
So you've got a block on the right hand side, and there's something sat in the middle. Looks like I don't know.
Is it orange?
No. So on the right hand side, we've got a wooden block. Yeah.
Yeah.
In the middle of that wooden block on the right hand side, what is that object?
Are you talking about this part?
No, the white part. Yeah, that where your mouse is now. Yeah. Oh, is that a hole? Is that a hole?
It's a hole. Yeah, it's a hole in the block.
Ah, right. Okay, I get it. Now I get it. Now I get it.
Like a Jenga type set or this.
Okay. And the block in the distance has got the same hole.
Yeah, they're exactly duplicates of each other.
Right. Okay. So what I would want you to do now is go get those two and show me a video of this where the blocks are next to each other and one moving away. One
moving away from the. Yeah, I know what you mean. You have two side by side.
Yeah. And and then show me this effect, because you would have found something new in modern optics photography and dimensional reality.
What do you mean?
I mean exactly what I said. If you show me that, I will make you famous.
I don't know what you mean. Like if I move the back, if I get two blocks.
No. So get 2 blocks next to each other, side by side, at the same distance from the camera.
One
and then, where the same setup as you've got now, so we can determine that the camera is on, looking at the top of the block.
Yeah.
And then move that block, one of them, all the way back, and then get this effect of it being lower.
Yeah, I can't. This is the point I'm making to you.
I know. This is a photo of that. I'm saying I would love to see a video of it.
Well, I can give you something before, and that's something I will do. Yeah, I will do that.
Yeah,
I will
brilliant.
Do that video.
Awesome.
I can give you
once you've done that, I would be incredibly interested. And Ranty's got me on Skype, so if in fact, I've got you on Skype now as well.
But this is why I'm showing you this, because my camera lens height is above. I can see over the. I'm actually seeing over that block. It's just I've zoomed to it from where I am. If I was zoomed back and took the photograph from back where it was, both those blocks would be very small in the foreground or in the background. They both would be small. I've zoomed forward to take the photograph, but my lens is actually over the top. I'm actually able to see over the top of that block, and that's why I've done this. I made a point of being able to see over the top.
No, that's fine. I'm gonna say this is evidence, and now what I'm wanting to verify this evidence is a video. Yes.
Well, I will do that, but I will also tell you something before I do that.
Okay.
Right? I've said it earlier twice. You didn't hear it, but I've said it on the show already twice. Samuel Rowbotham, in the debacle he had with the Bedford levels test, right? How he proved his point was when he looked into when he lined up his crosshairs of his telescope with the first marker. The problem was all the other markers in a straight line seemed to fall below it. Okay, so what he had to do, right? He knew. Well, it was angular size change. Things were getting smaller with distance. But it was being argued on the other side that it was that things were going over the curve of the Earth. So what he did is he lined up the first 2 markers with the crosshairs of his telescope. And he said, if I line up the first 2 markers with the crosshairs of my telescope and things fall away then I'll admit that it's not flat and that it's there's curvature and whatever. But when he lined up the first 2 markers, all the other markers stayed in line. And that's how he proved himself correct. That's how he proved himself correct in the Bedford levels. That was the final nail in the coffin. That's how he came out victorious there, because he proved angular size change.
No one's saying angular size change isn't a thing. It's a well-known thing in perspective. Thousands of people use it every day, architects and even people like myself. So that's never in any question.
See, my point to you here, I'm not picking on you, right? But it's that you're using 3D modeling software to model reality, whereas I'm...
wait a minute. To represent reality, yeah.
Yeah, I'm using physical pieces to model it. So what I'm doing is not going to have... the point I'm making is that what I'm doing, because I'm using physical pieces, is giving me a more realistic view. Whereas with modeling software, because I've used some of them, and I'm not adept at them like you are, but I've used them. And what I've noticed is that, when you move your camera up and down with the modeling software, what I noticed earlier on was the top of all when you were showing this on Jose's, the top of all the blocks you were using in the software you had them all lined up when you were looking at the top of them. But the bottoms of them were still coming in at an angle like this. So where was the perspective? Because what we see in reality is we see a horizon where the ground and the sky seem to meet. And that's because of things in the distance getting smaller with distance and angular size change. And obviously it becomes a diffraction limit. But the point I'm making is that in your 3D software, the top of what you were showing was like this, but the bottom of it was like this. But in reality, it's this and this. And that's what we see in reality when you see an horizon across the ocean on a clear day, when there's no big obstructions, you're seeing the sea and the sky appear to meet. So what I've noticed with 3D software is that 3D software does not give you an exact replica of reality. It's using mathematics to show it, as opposed to it. But my point is that you can't show reality as well with 3D software, modeling software, as you can with actual real modeling. If you understand what I mean.
No, we can simulate it incredibly closely and then measure those results against reality. So I often hear, oh, we don't live in a model, Dean, and that's never a claim. A model's entire purpose is to test predictions and your understanding on reality. So what I do, and I do this for the flat Earth as well. So I'll give you an example. I'll give you an example where it doesn't work on the flat Earth, for example, that I'm still trying to work on, and any suggestions would be awesome. So what I can do is I can take an observation of the moon, get Jose to take an observation of the moon in Florida, and get George to take an observation of the moon just south of the Canadian border at the exact same moment in time.
Yeah.
Now, when they send me those photos, the moon is at a different orientation. So let's say the largest crater is to the right for Jose, but then for George, it's kind of a diagonal, kind of, let's say 5 o'clock-ish. Yeah, 4:30, 5 o'clock. So I can take those two. These represent reality. Now what I can do is say, right, well, the model's purpose is for me to test those observations to see my understanding of the situation, to then measure it against reality. So what I can do, independent of inferring anything, is say, I'm going to put this on a flat plane. And I'm going to put the moon in any location I can to try and match this to see how this would work. And it doesn't. That's an issue. Now, before you go on, wait a minute, stop. Because the point about this is not this singular point. It's about a model. Now, what I can do is I can test it on a cube. I can test it on a sphere. Now, the issue with the sphere is it works and the flat plane didn't. It's not that model ever represented reality. It was a way for me to input variances and then measure them against reality so that I can comprehend or understand something which I might not necessarily be able to under normal circumstances, such as the shape and magnitude of the land mass that we reside on. But just to conclude on this, because I am actually, the only reason I came on here is I'm just finishing work, and I'm about to go to bed. But I just want to share my screen just to show you a little thing that should. I'm going to just unshare this now, just to respond to you about the moon thing. Well, I wasn't meant to. I was showing you what a model, I use a model
just
for.
To give you a response to that is that. There's two things I have to say about that. One is, for a start, I don't know what the moon is. Right, the moon is a pretty mysterious thing. I don't know how far it is, away it is for real, and what size it is, and all the rest of it.
I didn't say you did, Ryan.
Right?
Honestly.
No, I'm not trying to say that you said any of that.
Okay.
I'm not trying to misrepresent you. I'm just saying that so I don't seem like I'm talking as if I do know.
Okay.
Right, but what I'd say about it is that if you're looking at the moon from different locations on the Earth, then you're going to see it from different angles. So you're going to see it differently. Like if I'm in Australia, the moon will look kind of nearly half upside down. When I was living in Australia, the moon looked nearly half upside down from where it is. I'm in Ireland. I know that's not exactly because I was in about 33 degrees south.
No, I get it.
So it's not going to look exactly the same, but it did look different, and it's because I'm looking at it from a different angle. You know, it's like if you put drawings on a football and you sellotape the football to your ceiling and you look at that football from different angles, you're going to see.
Right. I know what you're saying. Now, the issue with this is it doesn't work on a flat Earth because of two aspects of it. Aspect number one is we both see, give or take, the expected in a spherical model, 5 degrees of variance. We both see the same side of the moon, and then the second premise is it is not distorted and it keeps a spherical shape, a circle in our vision.
They're
the issues. But again, it wasn't a point I was bringing up. I was bringing up how I use a model, and a model isn't supposed to represent reality, or you're not supposed to live on it. You just use it to test things.
I just want to say one thing before Glenn comes in. I
want to show this example because this is refraction, and this is the last thing.
Bring it on, share the screen.
Yeah, but you'll.
I can do.
This is something that will be of interest to you. What size is the horizon? What size is the circumference of the equator on your flat Earth model?
I don't know, whatever size it is, 24,000 odd miles or something. I don't know.
That's not correct. And the reason it's not correct is because a straight line distance, the only way to measure this, now this, I don't know for definite, if this is pseudoscience as well, because I don't know for definite if this is correct, is if the distances are correct. I can only go on what I'm being given as distances. Mm-hmm. But a straight line distance from the geographic North Pole to the equator is 6,210 miles, whereas the radius is 3,959.
Yes, I agree.
Right, so your diameter of that is going to be 12,420, and your circumference is going to be 38,998.8 miles, using degrees, 69 mile straight line statute degrees. So for you to get a flat Earth correct, you have to take a radius from let's just say if you want to do a model from. When I say correct, I don't even know if that's correct because I don't know much about the North Pole, where the exact geographic North Pole is or happens. So I'm only going by whatever we're told. But if you take a geographic from the geographic North Pole to 60. I'll
tell you what, Brian. Honestly, I don't mind having a conversation about this, and I'll talk to you about GPS satellites, which I'm acutely aware of as well, and things like that. But I just want to show this quickly before I go to bed because I am absolutely shattered. I don't mean to be an ass or anything. I've just said, I will contact you on Skype, Brian. I have actually just sent you a message as well.
Right. Go ahead, Stinger. Go.
Yeah. So what we've got here is we've got this lovely little bendy thing. You asked me to do this, Ranty, on Jose's show on how this would work. So we've got a curved surface. Now, if I switch cameras to... I've got a camera at the far left end, by the way. So if I switch cameras to the one that says observer. So here we have an observer. And you can see that... I don't know whether it shows up. You can see that I can faintly see that red square. Only faintly. In fact, I'll tell you what. For the sake of this, I'll make it a little bit wider.
We see it, yeah.
Okay. So now I'm going to put a layer of atmosphere in with an index of refraction where the angle of incidence would operate like we expect it to on a sphere Earth. And I'm going to show you the variances of it. So at the moment,
let me just clarify. This index of refraction only happens on a sphere Earth.
No. Sorry. I'm saying this is because it's on a curve. This is now what we expect to see. I can do it on a flat plane, but that's what I was showing on Jose's, and you wanted to see it on a curve. So this is what we would expect to see on a curve. So I'm going to increase the levels of density between us and that object, and the angle of incidence is going to remain the same. So it's going to be arcing downwards. Nothing to do with the curve. This is just on a curve. And what we start to see is this.
Okay.
So I can pull, and I've got a band of atmosphere here. We're not sat in the atmosphere. We're looking. I've got a dense band that we're starting to look through. And we can see that when I do this, it increases it and pulls it up. So I can make this appear somewhat flat if I wanted to. Now, the one thing that I haven't done here, and this is an open admission,
okay.
I am using... Wait a minute, just really quickly. I'm using Snell's law. I am not using Fermat's principle. So at the moment, I can't do a graduated effect. I have to do it in banding. But I will do a graduated effect when for lack of a better word, can be asked.
Okay, you do realise though that the Rumpus has dismissed Snell's law for observations.
So Snell's law deals with physical medium changes. Fermat's principle is more akin to the atmosphere, but the same principle of index of refraction, how refraction works, fits. It's just that Fermat's principle is immense maths and gradient based, whereas Snell's law is physical object and boundary based. So I have to on this free and open admission, I've used, but they both do the same thing. The rules stay the same. It's just the calculations are incredibly more complex with Fermat's principle. But I am going to include that in this, which would produce a much smoother result, and we wouldn't see the banding that we're seeing right now.
Okay, so what you've done here is you've increased refraction in your model.
Density.
So can you decrease refraction?
Yeah, that's decreased to back to nothing.
And what happens if you go the other way?
It does that and pulls the horizon close to us.
So it sinks the buildings?
Yeah.
Okay. So if you let's.
Oh, wait a minute. Yeah. So a good example. I'll tell you what. I'll make this a lot. I'll make the
whenever you guys ever do these kind of presentations, it always seems that the building's being loomed up from beyond the curve. Yeah.
Yeah. So exactly what you said there. So here we have little. Oops. Wait a minute. Give me a second. Here we have little to no refraction. This is the closest I would say that represents the geometric reality of what I'm seeing right now. Here we have lots of refraction where it's going up in the image and it's pulling the horizon up as well. And here we have the inverse of refraction where it's actually bending it down, translating it down in our view.
Okay, so can you model this on a flat plane and do the inverse of refraction on that?
I can, and are you ready for this?
I am.
Because I could just take away the bend. So the bend is that.
Okay.
I've just now taken away the bend, and if I go get the lattice, give me a second. So this is near enough the geometric reality. We're looking dead straight. We're looking dead straight down it now. In line with that object. You understand that, right?
Mm-hmm.
Now, if we automatically, if we take the principle that it's denser, the air is denser at the bottom and more dense at the top, then what we start to get is that.
Okay.
Dense at the bottom and and less dense at the top. That's what we get with atmospheric refraction. In inverse refraction, where we would see things like inferior mirages that we do see in bands, sometimes would make it do that.
Right, can you carry on increasing that, please, just for the audience to see?
Oh yeah, it just goes down.
So can you go back to normal and then show what would happen if we have an inverse of refraction on a flat plane? Just do it.
So the inverse of refraction is that it just goes down.
So it would disappear from the bottom up with just the inverse of refraction, yeah.
Yes.
And what weather conditions would be needed for the inverse of refraction? Can you explain? How warm would the water be and how cool would the air be?
Rumpus will be best for this, but the only time we see an inverse of refraction, and that is actually light bending upwards, would be in extreme temperature differentials on a band very close to the water, where it would also present. Someone's really loud, by the way.
Well, why would it be extreme differentials to have an inverse, but it wouldn't take a lot of differential to make a normal refraction?
Because you have to inverse the density layers. So air is more dense down at the bottom. Air is less dense.
Pressure is the answer, by the way.
There you go. Pressure.
Hello.
Yeah. So the issue with that is that has to be inversed. And now we do see that, but we only see it very localized in very small bands, and this is what your Fata Morgana is. And like I say, Rumpus is the person to take you through this. He absolutely is.
10 degrees. 10 degrees per kilometer lapse rate is the normal lapse rate you see sinking.
I thought it was 6.5 standard atmosphere.
No, that is standard atmosphere, but it would need to have a 10 degree temperature variation in order for sinking to occur.
Can this be demonstrated?
I thought that was 34, actually.
No. Well, that was based on. Let me get the citation. It's a university.
Yeah, I'd like to see that as an experiment being performed.
It is more a calculation.
I can take you through the calculations.
I'm not interested in a calculation. I want to see a physical
by empirical measurements.
Yeah, I'd like to see a physical experiment of that on the small scale. I mean, I've showed a miniature boat on a 600-foot lake that mimics reality, what we see and observe with boats. Surely it should be easy enough to get a tank of water and mimic the cooler air, the the warmer water, the warmer air, the cooler water, and show this effect.
But you just can't measure it, accurately enough on a small scale. What I was going to say is that there are instruments called interferometric refractometers, and they basically measure the refractive index of certain components of air, be it the temperature, the pressure, CO2 content, humidity, and they can, from these measurements, they can derive formulas such that you can derive or calculate a refractive index if you know the inputs, and the inputs being pressure, temperature, CO2, and humidity.
Yeah, but that's just a calculation. There's no demonstration.
Yeah, but derived from empirical measurements, right? That's the key.
Well, we need to see this empirical measurements. This is why I'm saying we need to do
interferometric refractometers. That's what they are.
We need to have testing done of this that can show that effect.
I'll try and find some papers where I can show the. So there's a paper which I cite to most people from Paul Sidor in 1996, and he basically took a whole bunch of other papers that did the empirical measurements of the refractive index, put them all together to come up with a formula that describes it all. You basically plug in the wavelength, pressure, humidity, temperature, and CO2, and it gives you a refractive index for those conditions. So if you then can take the conditions from the real world, plug them into the formula, you'll work out a refractive index for the surface, and then a refractive index for whatever your elevation is, and work out whether the density gradient is downwardly refracting or upwardly refracting.
So would this be similar to Walter Bislin's infinite slider?
Infinite slider, like I said when I was here an hour ago, it doesn't take a huge temperature gradient to get infinite over 6R.
Well, you see, before when you were saying about this infinite slider, fortunately it has a refraction index on the left. And what's interesting is when I asked the question, how much refraction would it need to sink, I was told that it would be quite a substantial amount more. However, what I find is when I use this refraction slider and I actually get a plus value of 0.16 or whatever here, and we get this amount. If I turn that to a negative, if I turn that to a minus, we get the opposite. We get the same drop going that way as we get going that way, and it's the same refraction going the other way. So it certainly isn't this 10-degree stuff that you were talking about before.
As far as I know, Walter Bislin does not use. So that number that you're sliding there is not an effective Earth radius. It's not like, so the number there you have 0.16. That is not, 1.16 over the radius.
Yeah,
that is a different. That's called the refraction coefficient. It's a different number entirely.
Yeah, I could move this anywhere. I could literally move it so far across to 0.5. As soon as I put a minus in front of that, and then go over this way.
That's not a radius multiplier. That's not a radius multiplier.
Yeah, but what I'm saying is that the refraction amounts, negative to plus, are exactly the same. It will either sink by that amount or it will grow by that amount in this calculation, in this model. Right? And when I asked before, I said, what's the sinking effects on a flat plane? If you inverse the refraction, I was told that it would take a 10-degree refraction before you see any kind of effects on that. And I don't see that in this model. This model says that you only need a small amount to start seeing this drop. Yeah?
I'd have to be familiar with the conversation, which I'm not, can't really comment. But I know that number. The number you're playing with is not a radius multiplier. It's the refraction coefficient, slightly different. You can translate it into a radius multiplier.
Okay, I forgot what we were talking about before.
It's getting late, Randy.
Sinking.
It really is.
Yeah, my mind is like, I'm sitting here, it's literally it's 4 degrees, the boiler broke down earlier today and it's absolutely freezing in here. I'm sat in a dressing gown, I've got a hat on,
Well, I'll put it this way: I've got my heating on full, and I don't think it's doing. And my heating's working, but I still don't think it's doing anything.
Same.
We just had our aircon fixed, so I'm happy.
Oh, shut up! Yeah, but you got fires heating the outside as well, haven't you?
Pretty much, yeah. Our visibility's pretty good though in the last couple of weeks.
For those after a good resource, though, I've just posted it up in the Skype chat. It's the calculator and also all about syncing. What?
Right. Yeah, so there we go. Lapse rate of 6.5.
That's standard atmosphere. That's not for that is not for actual syncing. Syncing has to have a 10 degree differential per kilometer.
The question we're answering here is at what point do so looming is objects appearing higher than they are in actuality, and syncing, we're agreeing, is they appear lower.
Yeah.
Which would imply a inverse density gradient. So like low density at the surface, higher density higher up. I'm fairly sure that happens at about 34 degrees per kilometre Celsius. And I'll use those equations that I talked about before to demonstrate it if you like.
Yeah, it differs in that citation there.
Yeah, all right.
San Diego State University.
Yeah, it's Andrew Young. Yeah.
Anyway, Ranty, thank you very much. I'm off, and I'm off to bed, and I'm going to turn up my heating even more. I shall maybe speak to you later.
Yeah.
See you.
No worries, no worries.
Take care.
Right, so if everyone's going, I'm going to show my hat and how I'm sat in this room, and it's bloody freezing.
Cold up north.
Everyone can have a little laugh at this hat. I'm sure there'll be some memes made, who knows. Right, but Ruhif, thanks very much for stopping by, and Gleam, excellent, thank you for stopping by as well. It's a shame I can't carry on for much longer, but it is getting to 3 a.m. now.
No worries. Yeah. Hit me up whenever you want, Ranty. I'll come in and play protagonist if you like.
No worries. Hey, listen, we've got the infinite over 6R.
Infinity over 6R.
Yeah, that's it. That'll do for tonight. If it's take one thing away, that will be the one.
Awesome. I would love to speak about that again. All right.
You like my little bobble? Oh, right, you can't see it. That's good.
You look like you're on a building site there. You look like someone who's working out on a building site. It'll be cold on you.
Honestly, it's freezing. It's freezing. Oh, and Brian, I didn't realise you were still there, mate. I am sorry. Brian, you've been here the whole time. Thanks all you guys for stopping by. Yeah, I'm gonna round out now. So thanks for stopping by.
On the board.
Salute.
Good night.
Yeah. So anyway, guys. So yeah, that was the call tonight. You heard everyone what they had to say. We had Globers come in, we had Flat Earthers come in. Everyone seemed to bring their own personal thing. I know Brian was incredibly hot about talking about the sun and the moon, and it was nice of Stingray to come in and do his little modelling there. So all very good for everybody that came in. Anyway, tomorrow we have Crow XE is coming to do a presentation tomorrow evening. And then on Tuesday, we have Brian back again, and he's going to be in a debate with a guy with a channel member. I think he's got 10,000 subscribers. So the guy that's coming in with 10,000 subscribers, the Glober, is coming in to challenge Brian for a one-on-one. This will be on Tuesday. So that's what I've got lined up so far this week. So I'm hoping you'll all be back tomorrow to tune in. In the meantime, me and my cold self will take myself off to bed, and I'll see you all in the next one.